Dear all, thank you very much for being here today. I guess a lot of people are still coming. The campus is kind of not very easy to understand, and it's changing every day. So to find a pathway to the end is quite complicated. So I guess people will continue to come. Nevertheless, we shall probably start now because of time constraints. So we are very happy to welcome you at this international conference dealing with underground storage and geoenergies, and a subtitle "Solution for Energy Transition." Well, just as introductory words, I would say that well, it's obvious for anyone that our technologically advanced societies need desperately energy, and the energy consumption is growing, although we should decay energy consumption. But it's not easy to continue the way of technological life we have without energy. And in this sense, we should at least reduce and stop consumption of the easiest energy available, which is carbon-based fossil energies, which means that we need massive transition towards kind of renewable geoenergies. Geoenergies is kind of, well, it's ambivalent because hydrocarbons are also a type of geoenergy, but they're just not renewable. So what we mean here is transition towards more renewable geoenergies. So it could be geothermal energy and wind and solar energy as well. But in any case, for the solar and wind energies, which are really expanding now, the key point is to be able to store the energy because of the intermittent nature of these renewable energies. And the most massive way of storing energy remains geological underground storage, whether it is, for example, synthetic gas storage or compressed air or hydrogen. We will see all along this conference different technologies and geoengineering solutions for underground storage of different type of energy sources and vectors. Okay, so I'm talking on behalf of the organizing committee, Laura Blanco-Martin, Philippe Cosenza, Jean SULEM, Andrei Constantinescu, who is director of our lab, Laboratoire de Mécanique, and Benoît Brouard, consulting. So Jean SULEM is professor at École des Ponts Chaussées. Laura Blanco is professor at École des Mines, and Philippe Cosenza is professor at the University of Poitiers. And this conference was sponsored mostly by the international interdisciplinary center E4C, Energy for Climate, which is based here on the IPP, Institut Polytechnique de Paris, and which exists for a couple of years now and is aiming at combined work from all the scientific disciplines, but not only economical disciplines too, sociological disciplines, in order to promote the most efficient ways in energy transition. And CFMR, Comité Français Mécanique des Roches, is also represented by Philippe Cosenza, who is the president of this committee. So, for this first day, we'll have, for this first day of summer school, here's the program we already have, but we'll have a starting talk by Professor Christian David, followed by a lecture by Professor Jean SULEM. And in the afternoon, so we'll continue with the presentation from Geosciences, and later in the afternoon, Brice LECAMPION. As I said, people will continue to arrive. So, well, let's leave this to the lecture.
Okay, first of all, thank you very much for the organizer for inviting me giving this talk. So it's a collaborative work with many people from our university, so CY Cergy University, formerly University of Cergy Ponts, changed name 3 years ago. Also people from a CSIRO in Perth, Australia, and the University of Mons in Belgium have collaborated to this work. So I will focus today on reservoir rocks with the idea to understand how reservoirs at depth are impacted by fluid extraction or fluid storage, like waste products, CO2 sequestration. And so here is the outline of my talk. So first I will start with some case studies just to present the kind of problems that we are dealing with. So first example is on hydrocarbon production in the ecofisc field and on CO2 storage projects in reservoirs. So I will not focus on CO2 storage because we will have a complete session on it tomorrow, I think. So, but I will talk very briefly about it also. Then I will switch to some background on mechanical compaction in reservoir rocks. So today we are talking about rocks with high porosity and which have fluids, which are interesting for human beings. So I will first say a few words about mechanical behavior and the brittle ductile transition in this kind of rocks, high porosity rocks, reservoir rocks. Critical pressure and failure envelopes in reservoir rocks. And then I will focus on the fluids. So what is the impact of fluid production and storage? And what is the physical-chemical impact of fluid rock interactions on the behavior of reservoirs? And then the last part of my presentation will focus on the weakening effects induced by fluid substitution. So how can we reproduce the fluid substitution processes in the lab, as we are doing in the field? I will show you some results both on sandstones and carbonate rocks. I will show that there is a link between these fluid rock interactions and surface properties of the rocks that you are dealing with. And finally, what is the impact of CO2 storage in reservoirs? So this is the outline of my talk. So let's start with the introduction, case studies. So if you have some questions, you can interrupt me, you can ask your questions whenever you want, no problem. So the first case study that I will show is ecofisc production, ecofisc field, which is in the North Sea, here. So England here. So it's a well-known reservoir which has been produced since the 70s. It's an offshore, obviously, so you have here platforms. And the geological setting is shown here. So the formation which has hydrocarbon to be produced is this one here. It's called the ecofisc chalk. It's a 300 meter the thickness is 300 meters. It's an anticline like this. You have about 3,000 meters of shales above, and the sea level, the sea floor is 70 meters below the sea level. So this is a reservoir which has been produced since a long time. So this is a figure comes from I don't have the reference here, from a paper published in 2006 which shows you the history of production of this Ecofisk field here. So there are many things in this diagram here. So in green you have the production rate through time, okay? So going from the beginning in the 70s here to 2007. In dashed line here you have the evolution of the pore pressure. In red you have the evolution of the subsidence rate. And in blue, you have the evolution of the water injection rate, which has been done in this. So to comment more precisely about this figure, so it's the same figure, but just highlighting some specific trend here. So production started in the 70s here, with an increasing production rate here, okay? And then obviously you are producing some oil from the reservoir, and obviously the pore pressure starts to decline, okay, from the initial value here, declining during the production. And then at some point in the 80s, they noticed that there was platforms were kind of sinking because of subsidence. And the subsidence is directly linked to the compaction of the reservoir because you are retrieving the hydrocarbons from the reservoir. So this is the subsidence rate here. So at this point, in the 80s, they figured out that something must be done to avoid this subsidence, because if the platforms are sinking, it's a major problem for the production, obviously. So then they decided to inject water into the reservoir. So it was the seawater that was injected in the reservoir with the idea to pump up the reservoir again, to increase the pressure in the reservoir and to decrease the compaction rate. Okay? So the idea was brilliant, but then they noticed that the subsidence rate, instead of decreasing when you injected the seawater, starts to increase. Okay? So that was a surprise, because mechanically, an increase in pore pressure should have decreased the subsidence rates, and in fact, it increased the subsidence rate. Okay, and so this was a surprise which needed to be explained. And finally, at the end, they stopped to inject water, so they decreased the injection rate. Pore pressure started to increase, and then finally the subsidence rates decreased. Okay, go back to the initial, to lower values than at the beginning. So we need to understand what's going on. So in the first stage here, before injecting the water, this is typically a mechanical effect, the pore pressure effect, which leads to the compaction. And in the second stage, which is here, the pressures are not changing a lot. So basically, this is a fluid substitution effect. You replace the oil by water, and then something is happening in the reservoir, which leads to an enhanced subsidence rate. Okay, so we need to understand what's going on here, and by doing lab experiments, for example, this is what I will show later in my talk. So, what happened during the production of this reservoir? So I will come back more in detail on this figure here, which is a failure envelope, the evolution of the production on a stress map like this. This is just to show here some pictures of the platforms in 1973. So it's the same platform which lies on the sea bottom, on the sea floor. And you can see that in 11 years, the platform has sunk, okay, because of the compaction, and you have lost about more than 10 meters. Okay, between here and here, you have a lowering of the seafloor due to the compaction, the subsidence, by about 10 meters. It's quite. So the oil companies had to spend a lot of money to rise again the platforms in order to continue the production. So this is the first case study, which is the starting point of my talk. The second one concerns CO2 storage. As I said, I will not focus specifically on CO2 storage, but anyway, so everybody knows that we need to limit the emission of greenhouse gases into the atmosphere. So one idea is to inject these fluids into in situ targets, which can be deep aquifers, which can be depleted oil gas or coal seams like this, in order to limit the quantity of emissions into the atmosphere. Okay? So this again is a kind of fluid substitution process, because you will change the fluids in the targets, in the reservoirs, and then you need to understand what's going on in such case. So actually, it's something which is already ongoing since many years in the Sleipner in North Sea again, in the Sleipner project. So in this here you have the offshore platform. You are producing gas in this formation here, and you also will pump some CO2, which will be directly injected in this saline aquifer here. So it's directly during production, you inject the CO2 not into the atmosphere, but into this saline aquifer. And then you can follow what's going on by doing some kind of seismic monitoring through years. And you can see, so this is the injection point here. So the CO2 is lighter than the water, so it rises up. And then you can follow the extension, the lateral extension of the CO2 in this kind of place. Okay, so these are my case studies. So now I'll switch to the second part of my talk, which is firstly to understand the mechanical behavior of these reservoirs. So everybody knows this kind of diagram, which is a brittle ductile transition in the Earth crust. So when in the upper crust, you have the mechanical strength, which is increasing with depth. Okay, and then at some point you have a transition. And starting from this, you have the mechanical strength, which is decreasing. So going from here to here, you have what is called the brittle ductile transition. This is what is going on in the crust, but for reservoir rocks which have a high porosity, you have this kind of figure in the upper crust as well. Okay, if you are dealing with high porosity rocks, this kind of phenomenon occurs at much shallower depth. Okay. So this is what we call the Christmas tree diagram, and the important thing is that in reservoir rocks, this transition again can occur at much shallower depth. Okay, so you don't need a lot of pressure stresses to cross the brittle ductile transition, as you will see in the following of my talk. So how can we study this brittle ductile transition? Classically, you can study this in the lab using a triaxial pressure vessel, like here. So you use the rock sample, which is located here. It will be subjected to two different stresses. So it's called triaxial, but it's not really triaxial. You have two different stresses: the axial stress sigma 1, which is the largest one, and the confining pressure, which is the stress sigma 3, which acts on the surface of the tank. And then testing reservoir rocks. So this is an example for sandstone. You have two kinds of behaviors. So if you are working at low values of the confining stress sigma 3, then you have a brittle behavior, okay, with a stress drop and the creation of fracture here. And if you study the volumetric evolution, the volumetric strain here, you have at some point you switch from compaction to dilation, and you have this kind of evolution. Okay, so this is a kind of typical behavior in the brittle field. If you do the same kind of experiments at higher confining pressure, then you will have this kind of behavior. Okay, so you have no fracture localization. You have a kind of homogeneous deformation patterns in your sample. And on the volumetric strain evolution, you don't see any dilation and you only have compaction. Okay. So there are two stresses that can be highlighted here. So the starts of the dilation, which is called the point C prime, and the onset of inelastic behavior, which is called C star. For these two kinds of behavior. So these are classical trends that you observe in these two a mechanism of deformation at low confining stress, brittle behavior, high confining stress, ductile behavior. So this is an example. So it's a paper by Pierre Bézuel, who studied the complete, characterized the complete behavior at different confining pressure of Vosges sandstone. So here you have the axial strain on x-axis and deviatory stress here, 4 different values of confining stress. Okay, going from atmospheric pressure here, it's a uniaxial test, and you increase the confining pressure up to 60 ampere. So what you see here is that the mechanical strength increases when you increase the confining pressure until this point, and the last point you see that the strength has reduced. Okay, from 50 to 60 MPa confining pressure, you see that the strength of the rock has decreased. If you look at the volumetric strain here, so you have volumetric strain here as a function of axial strain. Again, you see that the strength is increasing, and you switch from compaction to dilation, and at the end you only have compaction. Okay, that means that you have crossed the brittle ductile transition. Okay, so these guys here from uniaxial to 30 MPa confining pressure corresponds to the brittle field, and these guys here correspond to the ductile field. Okay. So one interesting way to plot this kind of data is to build what is called a QP plot or yield cap, failure envelope. There are different names for these kind of things. So on the x-axis, you plot the effective mean stress. Okay, so you calculate the average stress here, and you subtract the pore pressure, and here it's the differential stress, sigma 1 minus sigma 3, and you plot the points corresponding to the failure of your sample. Okay, so here there are many experiments, or each point is one experiment, and you have this kind of behavior here. In the brittle field, the strength is increasing, and when you go into the ductile field, you can see that the stress starts to decrease. Okay. So, if we want to focus to highlight some specific properties of the brittle and the ductile field, they are here. In the brittle field, you have the mechanical strength which increases with confinement. The elastic limit corresponds to stress C star, which is called shear-induced dilation. Okay. You have a peak stress followed by a stress drop. The volumetric strain first is compacting, and then you have dilation. The brittle field corresponds to the left part of the failure envelope. And finally, you have a fracture or a dilatant shear band, which forms during this kind of deformation. So, same kind of features for the ductile field. So this time you have the mechanical strength which decreases with confinement. The elastic limit corresponds to stress C star, which is called shear enhanced compaction. No stress drop is observed. Volumetric strain is always compacting, you don't have dilation. And the ductile field corresponds to the right part of the failure envelope, the part in which you have a negative slope. And finally, no strain localization fractures. You have deformation which is evenly distributed, uniformly distributed inside of your sample. And in between these two regimes, you have what is called this brittle ductile transition, which is not a sharp one. It's not a sharp stress at which you can say, I am at the transition. It's a kind of zone, okay, with some uncertainty on the stress, which we call the transition, brittle to ductile transition, okay? So it's something which can have some variability in stress. So to summarize on a QP plot, brittle field, you are in this regime here. You have formation of your fracture. Ductile field, you are in this part of the failure envelope. The samples looks schematically like this. And in between, you are in this transition zone, okay, in which the deformation often corresponds to compaction bands, which are shown like here. So I will not talk today about the compaction bands because of the limited time. Okay, so let's see some results, experimental results on this kind of analysis. So this is a plot. You have different sandstones which are here. So with different porosity, different grain size, okay? And you do this kind of analysis of brittle ductile behavior, and you plot all this in the QP plot. So you can see these failure envelopes, which are always the same kind of shape, but the size of this envelope changes a lot from one rock to another, okay? So this plot allows me also to introduce the concept of critical pressure. So the points that you have here on the x-axis correspond to a differential stress which is equal to 0. That means sigma 1 equals sigma 3. That means that these points here correspond to a failure under isotropic state of stress, a kind of hydrostatic state of stress. So how is this possible? So you do the same kind of experiment, but this time the sigma 1 is always equal to sigma 3, and you increase both stresses until failure. And you have this kind of plot. So we plot the volumetric strain here, the stress here, and you have this kind of evolution. At some point, you switch from the elastic behavior, you have an increase in the compaction, and this point here, this pressure here corresponds to what we call the critical pressure, P star. Okay. So on the former figure here, the P star, the values of P star for each sandstone are these values here, and you can see that it changes a lot from one sandstone, from one rock to the other. So what is controlling this critical pressure? So here you have several figures, again different sandstones, and each time I put the values of the porosity. And if you look carefully for the values of the P star, which corresponds to this strong enhancement of compaction, you can see that there is a kind of correlation between the value of P star and the porosity. The higher the porosity, the lower the critical pressure. So it's much easier to break a high porosity rock than a low porosity rock. And physically what is going on at the microstructure scale, what happens is that you have a phenomenon of grain crushing. So you are completely destroying your grains because the stress at the contact is too high. And you end up with this kind of figures in which you have some small fragments of your grains, and obviously this will lead to a sharp reduction in porosity. You lose completely the grain structure and you compact very efficiently your rock. This is what is going on at the critical pressure. So there is a model that we have been using for a long time. So it's a model developed by Zhang and Wang, which predicts the value of the P star, the critical pressure, as a function of a number of parameters, which are listed here. So porosity occurs here. R, it's the radius of the grains. In the model, you assume that the grains are spheres with a constant radius R. So E is the Young modulus of the grains, and Nu it's the Poisson coefficient, Poisson ratio of the grains. And then you have this parameter. Obviously, critical pressure is associated to the breaking of the grains. So there is some parameters which is related to fracture mechanics. So this is a K1C, the fracture toughness in mode 1, which occurs in these experiments, which appears in these experiments. And then we have this alpha parameter, which is not very well known. It's the ratio between the crack size in the grains and the grain size. So this is a parameter which is kind of not very well constrained, but anyway, it occurs in this equation here. So what we can say is that you have this coefficient, this parameter here, which is completely depending on the grain properties. Okay, so it depends on the nature of the grains and the toughness, fracture toughness of the grains. So for a given mineralogical composition, you can say that this parameter is kind of constant, and then you have critical pressure, which is a constant times the product of porosity and grain radius with a power law, which is -3/2. Okay. So the message to keep in mind is that P star is proportional to phi times R at the power -3/2. Okay. And it works quite good if you. Obviously, it depends on the mineralogical content of your rock. So you cannot mix carbonate rocks with sandstone. Okay. So this is a figure for siliciclastic rocks. I mean sandstones. But you also have some unconsolidated sand. You have some glass spheres, and you see that there is quite a nice trend between the critical pressure as a function of porosity times grain radius, and this red line here corresponds to this -3/2 power law. So the model is quite working good. You cannot use the same power law if you deal with carbonate rocks. Okay, you need to change the parameters, and the evolution is different. So now the idea is to say that the size of these envelopes here are strongly dependent on the value of P star. Okay? The higher the P star, the larger the envelope. So one idea is to say that the P star is kind of scaling factor for these failure envelopes. And what you can do is to normalize all this data with respect to the critical pressure. So you divide all this value here by the value of the critical pressure. That means that all the failure envelopes will arrive to a value corresponding to 1. Okay, if you do this kind of analysis. And this is the result that you get. So you have normalized all your stress values with respect to the corresponding critical pressure. So all the data arrive to 1 here. And you can see that there is kind of single evolution here, which can be fitted by this line here in the brittle field. And in the ductile field, it's a little bit more scattered, that you can consider that you have 2 envelopes which can fit all the data. So this is quite interesting because all these different sandstones plot on a single envelope here, if you do this normalization with respect to the critical pressure. So this is the equation of this line here in the brittle field. So it's a parabolic equation, okay? And on the other side, in the ductile field, these 2 envelopes here are ellipse, and these are the equations of the ellipse. These are the parameters that you need to use for these 2 kind of materials. If you want an average ellipse, you take the average of these 2 values, which is 0.6. So if you combine both kinds of analysis, it's quite interesting because if you have a rock, you know the porosity, you know the average grain size. From this plot, you can get the critical pressure, okay? And if you get the critical pressure, with this kind of plot, you can predict the failure stress either in the brittle field or in the ductile field, okay? For example, if you are doing triaxial experiments, you are following, in this kind of plot, you are following a straight line with slope equal to 3, and then you follow the slope, and then you can predict the failure using this kind of analysis. So it's quite kind of powerful because from the knowledge of porosity and grain size, you have the full mechanical behavior that you can predict with this kind of analysis. So if you want to test, you can do this kind of exercise that I'm doing with my students. So you take this plot here, you take this normalized envelope, and knowing the grain size and the porosity, you can predict the failure stress at 10 megapascal confinement stress or 70 megapascal confinement stress. Okay, it's kind of straightforward. Okay, so let's go back to my initial case study, which is the EcoFisk production history. So I separated again the mechanical effect here from the fluid substitution effect here, and now we are going to focus on this in the first stage, on this So what is the impact of fluid pressure variations on the mechanical behavior of reservoirs? This is completely, this behavior here is completely associated to the depletion of the reservoir, the pressure drop of the reservoir. So, what you need to do is to use the concept of effective stress. I think everybody knows that. You replace the stress by the effective stress, sigma star, using this relationship. So here I use the convention that compressive stresses are positive, so there's a minus sign here. Alpha is the BO coefficient, which is given by this relationship here. Often you use alpha equal 1 if you don't have much information about the reservoir. PF is the pore pressure, and this is the Kronecker symbol as usual. And you know that you see that this alpha is BO coefficient depends on the bulk modulus of the reservoir and on the bulk modulus of the grades. Okay? These are the two parameters which come into this formulation. So, to understand what's going on in different situations, so I plot here the failure envelope for a given rock, okay, with the brittle part, the ductile part here, okay. And first we are going to see what happens during a triaxial test. So in a triaxial test, you start by loading your sample hydrostatically. So you start with sigma 1 equals sigma 3. And then you will increase sigma 1, okay. And first you have, for one value of sigma 1, you have this Mohr circle. You keep on increasing sigma 1, and the Mohr circles are getting bigger and bigger until they hit the Mohr circle, hits the failure envelope here, and at this point you have your shear fracture. Okay? So this is what happens during an experiment at low confining pressure. If you do the same at high confining pressure, so sigma 3 is higher than in the previous case, then the envelope will hit this part of the failure envelope, and you will have a ductile failure by shear enhanced compression. So this is what happens schematically in a triaxial experiment, the specific effect of stresses during this kind of experiment. So now, what's happening if you introduce fluid pressure? If you consider variation of fluid pressure. First, what happens if you have an increase of fluid pressure, so plus delta PF? That means that in terms of effective stress, you are moving your Mohr circles to the left, and you will hit the failure envelope in the brittle part, and you will have some brittle fluid. So this is what happens when you are doing hydraulic fracturing. For example, fracking of unconventional reservoirs, okay, shale gas production. It also can happen if you inject waste fluids under pressure. Okay, if you inject waste fluid into a reservoir, you can have this kind of effect which can occur. So you need to calibrate the pressure in order not to fail to break your reservoir. Now, the reverse situation is when you have a decrease in fluid pressure. So this time you have minus delta PF, and this time the Mohr circles will go to the right, and you will hit the failure envelope in the ductile part, and you will have shear enhanced compression. So this kind of situation corresponds to the production of a hydrocarbon reservoir, like in EcoFisk. Okay, you are decreasing the pore pressure. And also, it corresponds to groundwater withdrawal. For example, this is what happens in the Venice Laguna. You are pumping water, and then the laguna is sinking because of this kind of phenomenon. Okay, so this the left part is quite well known. You just need to use effective stress. Now, what's going on in this part? So this has been less studied. Okay, it's not so well understood what happens here. So we are going to focus on this part from now on. So, what is the impact of fluid substitution? You are replacing oil by water, and something is happening in your reservoir. So, what is the impact of fluid substitution on the mechanical behavior of reservoirs? So, what happens is that these failure envelopes are not the same if you change the fluids in your reservoirs. So this is a study which has been done by Brice and collaborators in 2005. So he has, in the lab, he has built these failure envelopes for the same rock, the Ekofisk chalk, but with different fluids in the pores. And he found different envelopes, like these here. So the largest envelope was found for the dry chalk, okay, so you have air in the pores. And the smaller envelope was found when you have water in your pores, okay? And the intermediate case is the case when you have oil here, okay? And in our case, if we want to understand what's going on here, you need to compare the failure envelope to the oil case to the failure envelope to the water case, okay? And you can see that when you have water, the failure envelope has shrunk a lot. It's much smaller than the one initially when you have hydrocarbons in your reservoir. So this kind of analysis allows us to understand what happened during the production, during the water injection in the reservoir. So this is the same figure as before, but now we will go in a little farther. So production starts here. So you increase the effective stress because you deplete the pore pressure. So you are moving like here, and at some points you hit the failure envelope of the oil-saturated reservoir. Okay, so stage one is production with mechanical compaction. Okay, it's the left part of my diagram from before. You hit the oil cap here, and then you will have some enhanced. When you hit the envelope, you have some enhanced compaction like this. And then at this point, the stage two is, at this point, you do some water flooding, and you will end up with some kind of chemical compaction. Okay? And here, the stresses are not changing a lot, but you are just replacing the oil by water. And this is what happens. Without much change in effective stress, immediately you have some strong compaction, some loss of porosity, which is due to this kind of chemical compaction induced by water in the reservoir. So why do you have this kind of compaction? Because this point here is far away from the water cap, the cap corresponding to the reservoir with water in it. So you are immediately far away from the cap here, and this creates some instability, obviously. So this kind of phenomena occurs in carbonate rocks, but also in sandstones. So so we have seen that the Ekofisk chalk has become weaker, and this is what we call water weakening. But it also happens in other rocks, for example, sandstone. This is an example in Berea sandstone. You can see that the mechanical strength when you have water is lower than when you have air. And also, the elastic moduli are reduced in presence of water compared to air. So this is what we call the strength weakening, and this is what we call elastic weakening. In both cases, it is associated with the presence of water into the pore. So what does water weakening, where does water weakening come from? What is the reason for such kind of behavior? So one important, there are different causes for this, but the most important is the change in surface energy. So if we call gamma the surface energy, the weakening effect of water leads to a lower value of surface energy compared to oil and air. Okay, so this has been proven, it has been measured. You have a lower surface energy in presence of water compared to air and oil. So what is the consequence of that on the mechanical properties? So you remember that in the model, there is this parameter, K1C, the fracture toughness in mode 1, which comes in. And this parameter is directly related to the surface energy. And you can show that you have this relationship. K1C is proportional to the square root of the surface energy. Now, if you remember the model that I have shown before, in the model from Zhang and Wong, you have P star, which is proportional to K1C at the third power. So you replace K1C by this here, and you have a relationship between the critical pressure and the surface energy, okay? And if you compare two fluids, for example, if you compare water to oil here, you have this relationship, which is straightforward from this kind of analysis. The critical pressure in presence of water is equal to the critical pressure in presence of oil times the ratio of surface energies at the power 3/2. Okay? So if this one is lower than this one, you have a reduction of the critical pressure with water compared to oil. Okay? So this is a kind of nice explanation of this water weakening effect that can occur in reservoirs. I will show later, but there are other reasons which can explain this kind of weakening. Yes.
This explains the reduction of strength due to water, but how does water weakening explain the reduction in elastic moduli?
It's the same kind of relationship you have. You can relate the elastic moduli to surface energy. Okay. I didn't show it here, but there's also a relation between them. So, how can we reproduce this kind of effect in the lab? I mean, what happens during the EcoFisk production history. You can do that in the lab using a classical triaxial setup. And you can also use some acoustic monitoring by putting some acoustic emission transducers around the sample. So these are experiments that we have done with our colleagues at CSIRO. This is their triaxial machine here. This is the sample with the acoustic emission sensors around the sample here. And this is a schematic of the sample with all the transducers around here, around the sample. So these transducers, you can use them as passive transducers. That means that they will record the acoustic emission, or you can use it as active sensors to measure the evolution of the P-wave velocity along different paths. So you have different, you can do both with this kind of setup. So I will show you an experiment which has been done using this setup here. So first, two different experiments have been done. First, you need to do a triaxial experiment to know the strength of your rock. So this is the first scenario here. You need to characterize the strength in presence of air, oil, and water, and you do some kind of classical triaxial test. The second kind of experiments, you mimic what happens during the EcoFisk production. That means that you are doing under stress a fluid substitution experiment. So that's what we call here a fluid injection test. We inject water into a sample in which you have either air or oil to do this kind of fluid substitution experiment. So the stress paths are shown here. First, we are doing a kind of consolidation path here, hydrostatic consolidation up to 25 MPa. Then we go back at 5 MPa. Second, we saturate the sample. Depends if you are doing a dry test or an oil test here. And then you are doing your triaxial experiment until the sample fails, and you have what we call the dry strength or the oil saturated strength, and depending on the fluid that you have in your pot. So this is classical triaxial experiment to know the strength of your sample. Then the second kind of experiments, now that you know the strength of your sample, you load the sample triaxially until 80% of the dry strength, okay? And you keep the stress constant at this value here, and at this point, you inject your water into the sample, okay? So you inject your fluid at low pore pressure, because we want to minimize the effective pressure impact. We want a very small pressure here in order to change very little the effective stress during the experiment. So this is this is the cell that we are using in Cergy, same kind of experiment. The pressure vessel is a little bit smaller than the other one. The principle is the same. You put your samples between two pistons. So you have your sample here. The diameter is 40 millimeter, length 80 millimeter. And then you inject your water up until the top under constant stress. The stress is not changing during the injection of water. So the question that you want to solve is what kind of damage does the water induce in the rock sample? What kind of damage are you going to have? When, where, and how? Okay? This is the kind of questions that we are addressing. So the first experiment that we have done is on the sandstone, which is called the Sherwood sandstone. So it's the same Sherwood as in Robin Hood stories. It's in England, south of England here. And it's so here you have a picture of the sandstone. The properties are here: mineralogy, here heterogeneous mineralogy, porosity, permeability, and geomechanics properties here. So before doing our injection test, we have completely characterized the failure envelope here for this sandstone. And then we have done our triaxial experiments with the pores saturated with different fluids. Okay, and these are the results. So this is the mechanical behavior when the sample is dry. You have air in the pores. This is when you have oil in the pores, and this is when you have water in the pores. So you can see that the strength is significantly lower when you have water with respect to oil and dry. You can see that there is also a small effect when you go from air to oil, okay, which is not water weakening, obviously. It's a different kind of phenomenon which also occurs here. You have a small difference between the dry and the oil piece. So here you have the values of the elastic modulus, the strength, and you both have elastic weakening and strength weakening as shown before for this sandstone.
These are different samples. I mean, one you saturate with water, and the other one you saturate with oil. You don't replace one by one.
No, because they are broken. After each experiment, we are in the Bruton field. So the samples are broken. So these are experiments on 3 different samples. So here we show you a small video in which you will see what happens during fluid injection tests. So here you will see the evolution of stress, which is supposed to be constant in the experiment. Here you will see the evolution of strain. And in this column here, you will see the water, the level of water inside the sample, which will increase from the bottom to the top. And here, this is the sample with the sensors, acoustic emission sensors, and you will see the acoustic emission which are occurring during this experiment. So I need to start the comment est-ce que je fais? I don't know how to start the video. Sorry for this technical problem. Oh, sorry, the video is not working. I tried, but it doesn't start. So what you should have seen is what is here. So the stress is constant, and at some point you have the stress is decreasing. The system cannot hold the pressure anymore. At the same time, you have an increase in axial strain here. Okay, that means that when the water invaded the lower part of the sample, you had some kind of mechanical instabilities which completely destroyed the sample in the lower part where the water has started to invade. Okay? And this happens only in the lower part here. Okay? We injected until the top, but the top here never failed. Everything occurred here as soon as water invaded the sample. So we have done two experiments. This is when you inject water into a dry sample, saturated with air, and this is what you obtained when you have a kind of reservoir situation in which you have oil in the sample and you inject water. So you have the same kind of features which occur with some kind of deformation which is localized in the lower part and which occurs quite very soon in the injection process. The upper part of the sample never failed. Everything occurred in the lower part of the sample.
Excuse me.
Yes.
So, during the experiments, the time was given for the water to equilibrate, or the pressure of the pore pressure to equilibrate, or the loading was continuous? The loading rate was continuous.
The water was injected with a constant pressure, 0.5 MPa. Okay, so it means very low pressure compared to the stress which is applied to the rock. So you have very little effective stress variation during the injection. So everything is due to the replacement of oil by water. It's not a mechanical effect, it's really a fluid substitution effect which occurs. So from this study, we can conclude that water weakening can trigger mechanical instability in fluid substitution experiments, and again under constant stress. Okay? So we had this stress drop, but this is not what we wanted to do. It's the machine which cannot hold the pressure anymore. But we can consider that everything occurs at the constant pressure. So that means that when you are doing this kind of enhanced oil recovery operations in the field, that means that you inject water to push the oil towards the production well or to increase the pore pressure in the reservoir, you may be in trouble if you are in the situation where fluid substitution can trigger instability. Okay? So you have to be very careful when you are planning this kind of operation. You have to really identify the state of stress and see if you are in a stable situation or in an unstable situation. It's quite important. Okay, so second experiment that I will show you, which has been done by my former PhD student, David Jeremia. So he worked on carbonate rocks and specifically on two chalks from the Paris Basin, but in Mons, with our colleagues of the Mons University. So we collected different blocks of two kinds of chalks from this area here. So one is called the Aubourg chalk, which is a nice white chalk with properties here. So 100% calcite, porosity 43%, so it's really high porosity rock. Permeability is quite low for such a high porosity rock, but this is because it's a microporous rocks. The pores are very small. The size of the pores, it's around 0.3 micron, so microporous rocks. And the grain size, you have it here. So these have been collected from a quarry, open quarry. The second one comes from the same area, but it's another formation, and it's called, it has some fluoroapatite inside, so mineralogical content is more heterogeneous. Porosity around the same, but permeability is much higher than this one. the port radius is larger. Okay. So this one comes from an underground quarry because this chalk was exploited for his phosphate. You have some kind of operation to use this kind of. Okay, again, it's the same kind of test, same stress path, consolidation path, then triaxial loading, and then at the target differential stress, you inject your water. So same kind of process, but this time it has been done in our pressure vessel in Cergy, and we are doing this kind of injection tests on samples which are saturated either by oil or either by air. Okay, same kind of experiment. Okay, so we know before doing that we are doing classical triaxial experiments, so we know exactly the failure envelope. So this is a failure envelope for the dry case. Here you have critical pressure in the dry case, and here you have the failure envelope for the sample which is saturated with water. Okay, and the oil cap is not shown here, but the oil cap is something around here. It's a little lower than the dry case, but much larger than the wet case. Okay, and the solid line corresponds to the strength, and the dashed line corresponds to the yield. So we have both yield and strength. So the target in terms of stress for our injection tests is here. So these crosses here correspond to the injection tests. So what was the criterion to select this area here? We want to be above the failure envelope for the wet case and below the yield for the dry case. Okay? So we don't want the sample to yield before the test here. So this is the area that we targeted for the injection test here. Okay? And this is the kind of result that we got here. So again, so we inject water. Here you have the injected volume, the volume of water injected. Okay? And here you have the evolution of axial strain, differential stress, and again the same kind of things that we observe for the sandstone. At some time you have a strong acceleration of strain, okay, and a stress drop which corresponds to the failure of the rock. And the rock samples at the end of the experiments look like this. So we highlighted here these some kinds of features here which look like fracture, but the samples didn't break apart when you took it out of the pressure vessel. So this is the conditions for the experiments, and this is these are the conditions of the experiment. The failure here occurred when we injected about half the pore volume of the sample. Okay, so the sample was not completely filled with water. The water was probably close to the middle part of the sample. So we have done again different tests. So this is another experiment with other conditions here, and again you have failure in the lower part of the sample. Here you can see it very nicely. So again, this was supposed to be a video. You see the stuff turning around, but unfortunately we will not be able to see. So this is a summary of all the experiments, all the injection experiments that we have done. So we have done experiments as a function of, for different state of stress. What you have here on the x-axis is the fraction of the dry strength. So when you are here, that means this corresponds to the dry failure envelope. Okay, this is the strength of the dry sample here. Here, this is the strength for the water-saturated sample. So we are playing in between. This is the yield for the dry. So as I told before, we are playing in between these two limits. And here on the y-axis, you have the relative pore volume injection. If you have one, that means that you have injected the total pore volume into the sample. Okay? So one means that you have completely saturated your sample with the water. And what we observe is that there is a nice trend it's an exponential trend actually, between the amount of water that you need to induce failure and the stress ratio that you have here. And the same kind of exponential trend occurs for the time that you need to arrive to achieve the failure. So there is a nice systematic between the amount of water that you need to induce the mechanical instabilities and the stress ratio during your injection experiment. Okay? Obviously here you need 0 water to induce failure in the dry sample because you are at the dry stress of the dry sample here. So again, this is a summary of what I have told you before. The amount of injected water needed to trigger failure depends on the applied load. You have this exponential law that we see both for the CP chalk and the Aubourg chalk. And if you compare both curves here, you can easily see that this chalk here is much weaker than the other one. Okay, this chalk, the CP chalk, is much weaker than the other one if you compare this kind of. So here you can see this kind of deformation patterns during our experiments. So mostly it happens in the lower part of the sample. Here you have some deformation induced by the fluid substitution without any significant stress effect. So conclusion of this study on chalk, basically we observe the same kind of feature as for the sherbet sandstone, but with much more details. We can trigger some mechanical instabilities under constant stress just because of the fluid substitution. And this is something that we haven't suspected in the sandstone experiments. There is a systematic trend between the stress level and the amount of water that we need to trigger this instability. Okay, so now this is a slide to show you that there are other mechanisms of water weakening. Actually, there are many of them. So here, this is a kind of chemical effect here when you have some ions which are adsorbed at the surface here. I will not go into the details here. So this is another kind of explanation when you have some kind of suspensions and some bridges between the grains here. Here you can have some effect on strength if you have some bridges with small particles connecting the grains here, which can be removed when you have flow of water, for example. Here, this is explanation given by Gaznat, which accounts for attraction repulsive forces at the grain contacts here. And here again, we have surface energy, which I highlighted in red because we assume that this is a major effect in our experiment. Okay. I'm not saying that the other ones are not existing, but I am tempted to say that this one is the most efficient in the kind of experiments that we have done in our shop. So to go further, we tried to investigate the link between fluid rock interactions and surface properties. So we went into, we used different techniques to characterize the surface properties of our chalks. So again, here we have the failure envelopes for the dry chalks here, the water saturated chalks here. So this is nothing new. Both chalks show significant water weakening. The failure envelope is much lower in the water case compared to the dry case. And water weakening is mostly linked, this is our conclusion, in the reduction in surface energy. Again, this is what I have explained before. You have a relationship between the ratio of critical pressure and the ratio of surface energy. Okay? There is a ratio here, a systematic here between the values of the critical pressure here and the surface energy. So if we calculate this for our samples, we know the critical pressures. We have a surface energy ratio here, lambda is this one, surface energy ratio. It's 0.63 for the Aubourg chalk and 0.37 for the CP chalk. So this one is much lower than this one. That means that you have more water weakening effects in the CP chalk compared to the other one. This is what happens here. Actually, we have done some kind of compilation of different experiments on different chalks, different carbonate rocks, not only chalks. So these are the data that you found in the literature. And we plot here the ratio, the surface energy ratio, which have been inferred from the critical pressure every time. So we plot this surface energy ratio as a function of the specific surface area of these materials. And you can see that there is a trend here, okay? And our chalks here are close to this trend. And also the Sherwood sandstone, surprisingly, is close to this trend. Which shows that if you increase the specific surface area, then you enhance the water weakening effect due to this surface energy mechanism. Okay, so we see there is some kind of trend here. The reduction in surface energy is linked to the increase in specific surface area in carbonate rocks. So we have also done complementary experiments, not only injection tests, but we have tested different mechanical parameters. So we have done uniaxial tests, we have done Brazilian tests to have the tensile strength. We have done different trisal tests here, hydrostatic tests, and also the semicircular bending test to get the K1C, the fracture toughness, in this kind of experiment here. So we have done this systematically on the dry rock and on the water saturated rock. Okay, so the values are here, and this is what we call the wet to dry ratio, which is defined here. It's the property in saturated condition divided by the property in dry condition. Okay, so if it is lower than 1, that means that you have water weakening. Okay, so the ratio you have it here. So you can see that it's significantly lower than 1. So for all these different mechanical parameters, you have weakening, which is induced. Okay. For the CP chalk, same properties here, and in general, you have values which are lower than this one. You have some exceptions, but generally you have lower values here. That means that again, this chalk is weaker than the other one in terms of water weakening effects. So this is the same data as in the table before, but which are shown as a kind of chart diagram here. So for these different properties here, we have the wet to dry ratio here, which in all the cases is significantly lower than 1. But you can see that depending on the properties, this dry to wet ratio or wet to dry ratio depends on the property. It's not always the same. And if you compare this diagram for the CP compared to this one, you can see that the effect, water weakening effect here is enhanced compared to the other one. We also tried to measure the energies, the surface energy. So there are different techniques to do that. You have direct techniques and indirect techniques. So one way to access the surface energy is to use the relation which defines the equilibrium of a drop of liquid on the surface, okay? But you can imagine that this kind of experiment, it's difficult to do it for a porous rock, because if you put a drop of water on the surface or on a dry surface of a chalk, it will immediately absorb into the pore space. So one way to avoid this kind of thing is when you do this kind of experiment, before you saturate your pores with epoxy. And then you correct for the epoxy effect. Okay? So, but if you do that, you have some theories which can give you the surface energy for this kind of experiment. Another way to have access to the surface energy is to use atomic force microscopy. So I don't know if you know this property. It's a property in which you have a small tip here, which will tap sinusoidally on the surface, and which will give you different parameters. One parameter is the adhesion force, which is here, and the surface energy depends on this adhesion force here. R is the size of the tip, which is probing the surface. And finally, you have also this relationship, which gives you the surface energy, which depends on the Young modulus and the fracture toughness of your material. So you can calculate your surface energy using this relationship here. So the values are here, and the ratio, the surface energy ratio between saturate and dry here are given. And you can see that we have higher values than what we inferred from the critical pressure. Critical pressure, we were about 0.6 down to 0.4 for the two choices. And here you can see that we have higher values using these techniques here both for the O group and for the CP choke. Okay. So it's difficult to compare these two kind of analysis, but what is obvious here is that the ratio is significantly lower than 1, which validates the fact that surface energy has a strong control in our experiment. Okay, so I will just finish on some results for CO2 storage. What can we do in the lab to study the impact of CO2 storage? So obviously, what happens? It's a little bit more complicated when you inject water, because you have this kind of relation here, chemical reactions here, which will increase the pH of the fluid that you inject into the reservoir. So if you increase the pH, then you will have some kind of acidification effect, which can lead to the dissolution of your grains, of your rock. So you have fluid substitution, but the fluid that you inject has some aggressive properties with respect to the solid grains. Okay, so you have enhanced physical chemical interactions with the solid fluid. So there are different things which can happen depending on the distance from the injecting boreholes. So this comes from the thesis of Louis Zinsmeister, Alexander knows well. And so you have different kind of phenomena. Close to the borehole, you can have some drying phenomena during the injection. And here you have some heterogeneous reactive zone, homogeneous reactive zone here. And finally, at some distance, you will find the formation properties, because the plume has not yet reached this part of the reservoir. So just in 2 slides, what kind of effects can we expect? It depends on 2 things. One thing is the fluid velocity. So one thing is the fluid velocity here, and the other thing is the reactivity of the fluid that you inject. And on this diagram, depending where you are located in this diagram, you can have different kind of features. You can have uniform dissolution, you can have compact dissolution, or you can have creation of wormholes. And this corresponds basically to samples which look like this after the experiment. So here you have, it's following the uniform case, and here you have created some large channels corresponding to what you call wormholes. So I will not go further, because we will have a session dedicated to CO2 injection, and probably we will talk with some more detailed features will be presented there. Just the kind of experiments that you can do to analyze the effect of CO2 injection. You will use a cell like this, in which you can inject different fluids, okay, and you analyze the evolution of the system through time. And this is the result. For example, for different cycles, these cycles of CO2 injection, then brine injection, you do some cycles like that. And basically, you can see that starting from the initial porosity profile as a function of the distance from the entrance of the core to the outlet. So this is the initial case, the raw sample without any injection. And you can see that when you increase the cycles of CO2 and brine injection, when you increase the cycles, you can see that the porosity is increasing. But you can also see that there is no change in profile, in the shape of the profile, no significant change in the profile. That means that probably you are not generating this kind of wormholes. It's more here in this kind of situation, it's more a kind of uniform dissolution of your grains due to the injection of CO2. So this is the kind of thing that you can analyze. And if you want to link this to the mechanical properties, then you do triaxial experiments at different confining pressure as usual. And you can see that, so the red one is you have done 6 cycles, blue you have done 3 cycles, and the black is the intact rock. You can see that when you increase the number of cycles, you have a decrease in the strength of the rock. Okay? That means that this dissolution of your grains, the modification of the contacts will change your mechanical property. And you can see this for different confining pressure as shown here. Okay, so I come to the conclusion. Timing is quite good, huh? So my conclusions are here. It's important to account for the nature of the pore fluid to assess the mechanical behavior of reservoir rocks. So it's something which is important because people usually focus on the pressure effect. Okay, you need to know the pore pressure and so on. It's also important to know the chemical effect of the fluid that you have in your pores. Water has a significant mechanical weakening effect in sandstones and carbonate rocks. It can trigger mechanical instabilities without changes in the applied stress. Okay. In all our experiments, we take care to inject at very low pressure in order to minimize the effective pressure effect. The weakening effect of water is linked to the lower surface energy of the solid-fluid interface. We also showed that there is a trend between the specific surface area, which is that the higher the surface area, the higher the reduction in surface energy. This is what we have shown from our compilation. And finally, in CO2 injection operation, fluid-rock interactions can be enhanced due to the fluid acidification, as I have shown. Here you have some references of, from which all these data come from. So if you are interested, you can have a look to these methods. Okay, that's all. Thank you for your attention.
Thank you very much, Christian. Well, welcome for questions. We have room for that. We planned half an hour between the presentation and the next one, so if you have questions, please go ahead.
In your study, you study a sandstone rock, and it has a certain proportion of clay inside. Are there any study on the role of the proportion of clay with the resistance of the rock?
It's a good point. We have done that. We have selected one rock to do this kind of experiment. But it would be interesting to make a systematic analysis with the amount of clays, the nature of clays, because you can have some swelling clays and other clays which are not swelling. I guess that the effect would be different. So, but we haven't done this kind of thing.
In fact, I suppose the role of water and clay is important in the case.
Sure. Can you go back to the next slide before this one? Yes, on this cube.
This one?
Next one. Yes, this one. On the first, why do you have a two rate?
Probably they have done 2 experiments. I don't know.
Into and
But different results.
different.
Christian, you showed different weakening degree in the samples for which you inject water in the dried sample, or when you replace the oil by the water. So could you say a little more on the different mechanisms that you have, wetting and non-wetting fluid, and the replacement and the interface between the two, which are also triggering mechanisms of
Yes, we haven't done much about the study of if you are wetting, non-wetting. It's very important. Recently, we have done another round of experiments on another chalk, and then we got results which are completely out of trend from what you have here. And we suspect that there was, although we injected water in these experiments, probably the sample was still oil wet, and we didn't see much weakening during our experiments in this chalk. So it works quite fine for what I have shown on this over chalk and CP chalk. But there are some cases in which you can have some trouble when you are dealing with, is the solid oil wet or is it water wet? It's something also that you have to consider. And we don't have, I didn't show it, but we don't really have a control on how is the waterfront. Is it planar? Is it do you have some kind of fingering or things like this? So we don't have any information about it. I will show some results in my talk on Thursday when we are doing some acoustic monitoring. Then we can more or less say what happens about the shape of the waterfront.
I have a question. What I understand is that the free type has a big influence. So my question is that, like during all these experiments, for example, the experiment to determine the failure envelope, the toughness test, and also like loading test, do you consider that the pressure is uniform inside the sample? What would be the role of the viscous flow for different free types?
You are talking about these different experiments? These ones? We have done
and also before, like you assume that pressure, how you calculate the effective pressure, effective stress, like the per pressure is uniform, considered uniform inside the sample.
We control the pressure at the bottom of the sample. We have a pump, so we just say the pump to stay. You keep this pressure constant. Okay. Now, if you have some heterogeneity in your samples, you can have some. You could have some small variation of the flow pressure inside the sample. We don't control it. What we control is the pressure at the entrance, at the bottom part of it, to push the water inside the sample.
This is the replacement test, right?
Yes.
But before, like for the determining the failure envelope with different free types.
These are classical triaxial experiments in which you control. You say the flow pressure has to be constant. So you control.
So you assume that the flow pressure is uniform inside the sample.
Yeah.
And you think like during this kind of task, during the loading stage, the loading rate will have an impact on this flow pressure distribution on the sample, or and also the final material strength results.
I mean, the strain rate can have some influence on the flow pressure. We are doing our experiments at a classical low strain rate, so we don't expect any problem. Viscous flow, which could change the pressure. We don't expect that.
I have another question, which is related. Could you explain more about the role of the toughness, how it got involved into this formulation?
The fracture toughness?
Yeah, fracture toughness. What I understand is kind of the breakage of the grains, right?
Yes.
But this is like it belongs to solid properties. How can we relate it to different fluid types?
In the model,
the surface energy due to the different types of fluid, how much percentage you will consider to contribute to the final change of the toughness?
when I link the critical pressure to the fracture toughness through this model, there are a lot of assumptions in this model. I didn't go through that. You need to have frames with the same size, a random assembly of spheres and so on. And one assumption is that each grain initially has some small cracks. Okay? And you break your grains when these cracks are propagated. Okay? So that means that you can link the critical pressure to the stress level at which these cracks are propagated. And this stress level depends on the K1C, on the fracture toughness. This is how it comes in. Okay? As K1C depends on surface energy, if you have different fluids in contact with the solid, you will have different kind of behaviors.
You talked about the effect of pH when you inject CO2. Do you have an idea of what would be the impact of temperature gradients when you're inside the subsurface? Considering that you did, I guess, all the tests at ambient temperature.
These are not my experiments. It's just to show you quickly what you can expect. But I would suggest that you ask this question to Philippe Braun. You are doing the talk on CO2. So please ask the question.
You mentioned the acoustic emission sensor during your experiment. Could you comment a little bit if you had acoustic emissions during the water flooding or injection?
So this was a video that didn't work. Okay, so when on the video you would have seen the water level which goes up. Okay? And when it goes up in the lower part of the sample, you start to see some acoustic emission forming in the sensor. Okay? So there is a correlation between the level of water into the sample and the acoustic emission, which is consistent with the deformation that you see on the sample after the experiment. Everything is located in the lower part. So you have a nice image between acoustic emission and deformation. You can see. But on chalk, we don't see any acoustic emission. Okay? So I didn't show anything on acoustic emission in chalk because you don't see any. Either in tractor experiments or in fluid injection, we don't see acoustic emission. There's no way to use this information to characterize better the behavior. So here you have just as the acoustic emission, you don't see the water level, but typically here, when you have all this kind of stuff which appears, this is this mechanical instability which occurred in the sample. And basically everything is located in the lower part of the sample during the experiment. So in the video that I wanted to show, you have the simultaneous evolution of strain, water level, and acoustic emission. And it's quite a nice correlation. Please.
So Christian, may I return to the question posed by one of our colleagues here about the effect of the different fluids on the elastic stiffness of the sandstone. So I just wanted to ask you on the basis of our own experience with these things. Very often we find that the elastic modulus is actually only an apparent elastic modulus, and that part of the deformation is often irreversible, and that it's actually creep effects that occur during the apparent elastic line. It's roughly linear. It's actually creep effects which lead to the reduction of the modulus when you inject water when you use water as a core fluid compared with oil. Is that a really different result from your experiments?
We haven't done much about the elastic weakening. We're more focusing on the strength.
So my answer to your question would be, it's not actually elastic, probably. Yeah, the effect you see is probably not really elastic. It's probably some irreversible deformation, which is reducing the apparent stiffness.
your last question.
I have a question on the failure envelopes that you normalized by P star. Does this also work for the chalks or other rocks, or only for the sandstones?
I mean, in the parameters of the models, there are many parameters which depend on the grades. So you cannot mix carbonate rocks and rocks which are mostly based on the silica composition. The toughness is different, the Young modulus is different, the Poisson ratio is different, so you cannot mix. Okay? But there are there are some people who have done the same kind of analysis just focusing on carbonate rocks. So there is a work by Patrick Beau, he has published a paper in which he shows, he analyzed the failure envelope for carbonate rocks but using a different law. So you can find this in the literature, how to change this law and adapt it to carbonate rocks.
Is there some physical explanation about the difference of the upper part of the envelopes? Like some micromechanical explanations why some have
What do you mean? I don't understand.
Are there some micromechanical explanations why some of the sandstones they have a higher envelope than the others? Like there was the top part which was not the same for all sandstones.
In the ductile regime, we have some scatter.
The transition regime.
Yeah, it's hard to say. This is a region where you have some compaction bands which are mechanisms are quite different from brittle failure. So it's hard to say. We didn't really analyze this.
Okay, so we'll continue this morning session with a lecture of Professor SULEM.
Okay, thank you, Alexandre. Good morning, everyone, and thank you for attending this course. So we have seen this morning in the previous talk of Christian David that very often failure occurs in not diffuse deformation mode, but rather localized deformation modes. So this will be the topic of my talk this morning. And as it is a school, I would like first to present some basis about the analysis, the theoretical analysis of strain localization, and then discuss what we have seen also in the previous talk. What is the effect of interaction of the solid bodies with fluids, interaction in terms of chemical reactions that can occur because of the flow of reactive fluid, and also the effect of temperature in the occurrence of such features of strain localization. So deformation bands in geomechanics are ubiquitous structures that are observed at a very large range of scales, from the sub-millimetric scale, typically the grain size, up to the kilometric scale, corresponding to very large structures such as faults. They induce a strong heterogeneity, both in the strength and in the physical properties, in terms, for example, of porosity and permeability, and therefore they play a major role in many geosystems, in the failure of engineering structures that we observe in foundation engineering, in borehole stability, in the flow of fluid, and with all applications related to the topic of the conference this week, and also in the nucleation of earthquakes and landslides. And this is a key point also of my talk today, is that strain localization, as we see, is a multi-scale process and also a multi-physics process. Just to illustrate what type of objects we are talking about, this is the typical shear zone that is observed at the failure of tried sample. This is spontaneous sandstone. If we look under the microscope
on this zone, we observe this very intense crushing of the grains inside the band, which has, you see, the thickness of few grains. And it's remarkable to see how this structure, which is observed in the laboratory, is very similar to what is observed in the field. This is a fault zone, the whole sandstone, and you see the scale here. The grain size of continuous sandstone is about 200 microns. So you see similar features and similar scale also. This is a photograph that was given to me by Yanis Vardoulakis of shear bands, conjugate faults. You see at small scale in perlite, or you see shear failure also observed in cavity failure experiments. Also, a similar type of strain localization is obtained, for example, in shear experiments. This is a rotary shear device where you see here a sample, cylindrical sample is shared by the rotation of one part of the device here. And what is observed is strain localization. Also, you see a localization of the damage. Again, we see this intense crushing. Here, it's an example of a carbonate fault gouge. There is also evidence that, especially in faults, strain localization is accompanied with very high temperature increase. This is an example of first fault in central Italy. It's documented in the paper of Polytechnique, Spolito. And what is observed here is what is called principal slip zone. You see that it has a thickness of only a few hundreds of microns, and such structures has accommodated a very large range of displacement, here several kilometers. And evidence of very high temperature is given by the fact that there was some mineral decomposition in terms of decomposition of carbonates, rocks, and also dehydration of clays. Also, this was mentioned in the previous talk also, the specific objects corresponding to compaction bands. This is compaction bands in sandstone formation. These are famous pictures that you find easily on the internet. And you see, because of the erosion, these zones corresponding to these compaction bands, where the intense crushing and compaction has led to a more resistant material, leave these features. And in an experiment obtained by Jérôme Fortin some years ago, similar type of structures. These are not interpreted as shear bands, but compaction bands, as they are forming in the direction normal to the principal major stress. And it is characterized again with very high grain crushing. So let's start from the theoretical basis, and those of you who are interested can go further in looking at the book we wrote almost 30 years ago with my great colleague and friend, the late Professor Vardoulakis. And so we are all used to the concept of failure envelope. We have seen in the previous talk that we can have some complex failure envelopes that could capture both shear failure but also compaction failure. In geotechnical engineering, we use commonly the concept of Coulomb analysis. And it's very useful because we have at the same time the limit stress, which is used in limit analysis, but also the orientation of the failure plane. And we distinguish between compression and extension and the famous formula of P/4 plus or minus phi/2, which gives the orientation as compared to the major axial stress here. So you see that in this analysis, the orientation of the failure plane is deduced from a purely statistical consideration. It's related to the locus of the maximum shear stress. It is deduced from the knowledge of only one parameter, typically the internal friction angle of the material. And although it's very useful, it's not exactly what is observed both in the laboratory and also in the field. The fact that failure does not depend only on one material parameter, but can depend on the whole loading path, and especially also depends on the whole deformation process. And you observe that failure should rather be described as the formation and the propagation of zones of localized shear deformation. And this process can be seen as an instability that can be predicted not only by one material parameter, but by considering the whole pre-failure constitutive behavior of the material. So the idea here is to go a little beyond classical limit analysis as used in geotechnical engineering or in other applications, and consider mathematical concepts of uniqueness, bifurcation, to study failure of materials. So, first we have to maybe clarify some words and some vocabulary, because the term instability is very much used with different meanings. What is called Lyapunov stability is considering an equilibrium state, looking at the evolution in time of a small perturbation that is given to the system. We are speaking of the system, and whether this perturbation will decrease, vanish in time, or rather increase in time, defines the difference between a stable system or an unstable system. So perturbation analysis to check the Lyapunov stability. Now there's, another concept, which is the concept of bifurcation. Bifurcation is a mathematical term related to loss of uniqueness of the solution of a given boundary value problem. In our application, we are interested in the evolution of the system up to some point, and we see the next increment and look if the deformation mode is the same or if it bifurcates in a different way. So the two first notions refer to a mechanical system. And then there is also the word of material instability, as you can find in the literature. And now the mechanical system that we are looking at is a material element. It's a representative elementary body with homogeneous state of stress and strain. And we look at a spontaneous deformation mode in the next loading increment. So it can be seen also as bifurcation, but here at the scale of the representative elementary volume. Okay? So, just to start with an example and to understand maybe this notion of loss of uniqueness, I start with the example of an infinite layer which is shared by applying displacement here at constant rate. So we have the shear strain, volumetric strain from the momentum balance equilibrium equation. We obtain the state of stress, which is trivial, it's very uniform, and the deformation also is simple. We have a shear strain, which is just the imposed displacement divided by the height of the layer. So we assume that we have brought the deformation up to some deformation state, gamma dot, in an homogeneous way, and we look for the possibility of non-homogeneous deformation in the next step, in the next increment. And for that, we use some constitutive models, here elastoplastic constitutive equations. So we have the shear strain rate, which is the sum of the elastic part and the plastic part, and the plastic part is given using here a more Coulomb yield criterion. H is the hardening modulus. So we have the elastic part here, and then the plastic part. Now, for elastoplastic solids, we know that the response differs in loading and unloading. In loading, we have the formation of additional plastic strain, and we have here the tangent modulus of the shear strain curve, which is given simply by this value, h over 1 plus h over j. Whereas if we unload elastically, and so the modulus is simply the elastic shear modulus. So now we are looking for the equilibrium. If if a shear band is forming, inside the shear band we have loading, outside the shear band we have unloading. So just by writing that the shear stress is the same in both sides of the band, we obtain this equality. And obviously, for that, if H, this is the plastic shear modulus, is equal to 0, corresponding to the peak here, then the shear rate deformation outside the band is 0. So in other words, at the onset of localization, the material outside the band is reacting or behaves as a rigid solid. This is one point. Now, the second point that I want to mention is that past the peak, the deformation mode is no more unique. Let's assume that we have a localization zone here, which has a thickness, and eta is the ratio of the thickness of the band as compared to the thickness of the layer. So again, we write the rate of displacement as the sum of these two components. We write the equilibrium, and after some algebra, we obtain the relation between the shear stress rate and the displacement rate, exactly what we need in order to trace in the plane tau u, the shear stress displacement, to trace the response beyond the peak. And you see that here, this response depends on the thickness eta of the band. So if the band is thinner, then this slope is strong. And we have here, we recognize some critical state for which the slope is vertical, which means that a quasi-static solution is not possible if you see the ratio of the plastic modulus in the softening regime, H is negative, is smaller than some value. So, in summary, on this example, what we have learned is that non-homogeneous deformation occurs past the peak of the shear stress versus shear strain curve. The non-homogeneous deformation exists and is not unique, and different solutions with different shear band widths or multiple shear bands, also we could imagine the structure of multiple shear bands can exist. In the post-peak regime, we have deformation which localize inside the shear band, whereas we have elastic and loading outside. And past the peak, the load versus displacement curve is not unique and depends upon the thickness of the vent. This is very important when we are calibrating constitutive loads, because we have to be careful when using the post-peak data to calibrate the load, because we see that it's not an intrinsic property of the material, it depends upon the thickness of the shear bed. And as we'll see in due course of the talk, we cannot get information on the number and the width of the shear bands when using simple constitutive model, as I'm shown here, simple elastoplastic Coulomb, without some information on the material length, the length which will scale the actual shear band thickness. Okay, so let's go now a little further and see how we can find the condition of strain localization in 3D configuration. And for that, develop what is called the deformation band model that was first introduced by Hill and then Jean Mandel, and also a very important paper of John Bounicki and Jim Rice, and also the early work of Yanis Vardoulakis. So here, what is called a shear band is a zone of thickness here 2 dB, corresponding to, which is limited by a surface here. And what we are looking at is the possibility of the discontinuity across this surface of the strain field. I insist on the fact that what we are looking at is the discontinuity of the strain, not of the displacement. We are not looking at the formation of the crack. The material is continuous, the displacement is continuous. What we are looking at is the discontinuity of the strain. And this has important consequences because this is how we get what is called the kinematical compatibility condition. When we know in mathematics, if a function is continuous across a border, a line, or a surface, then its tangential derivative is also continuous. Only the normal component is discontinuous. So this is what we write here. The project here means the jump across the shear band boundary. So the jump of the displacement is 0, and the jump of the gradient of the displacement is parallel to the normal to the bend. Now we have also to write the equilibrium. So the tractions in the two parts of the boundary are equilibrated, they are equal. So in other words, the discontinuity here of the increment of the shear of the stress projected on the normal is 0. And what we need as an additional information is the constitutive law, which relates the increment of stress and the increment of the gradient of the increment of the displacement. And C here is a constitutive tensor, for example, that we obtain from elastoplasticity. Now, to be more rigorous, we have to consider two types of bifurcation. The first one is called discontinuous. This is exactly the first example we have seen before, which is the case when we consider elastoplasticity, that we have seen that the constitutive behavior inside and outside the band is different. Outside the band there is elastic unloading, inside the band there is plastic loading. And the case for which we have the same constitutive tensor inside and outside. And this was studied in several papers in the 80s, and it was demonstrated that continuous bifurcation precedes discontinuous bifurcation, although they are very near. So if we look at continuous bifurcation, this is to assume that the constitutive tensor is the same inside and outside the band. We have a lower band of the true conditions of strain configuration. Okay, so if we assume that the discontinuity of the constitutive tensor is 0, and we do some algebra, we obtain that this is what we are looking for. We write here the equilibrium, and we replace here the increment of the stress using the constitutive law. And we are looking for non-trivial solution for this linear system. The unknowns are gk. If gk is non-zero, then it's possible to have such features. What we recognize here, this tensor is the acoustic tensor. If you look at the velocity of waves that propagate in a solid, you can calculate this in the direction n. What we obtain is that it is given by this tensor. You see that it depends on the constitutive tensor and also the direction. We know that, for example, if we analyze elastic waves for which we relate the speed of the waves to the elastic module. So, we have obtained what is called the strain localization criterion, the condition for existence of a weak discontinuity. Weak means that it's not a discontinuity of the material or discontinuity of the displacement, but a discontinuity of its derivative, of its gradient. It is that the acoustic tensor, its determinant is 0. The acoustic tensor is singular. Now, we can go further, and this is eigenvalue problem. We can compute also the eigenvectors J. And for a given problem, we can distinguish different situations. We have two extreme situations. N and J are unit vectors, so the scalar product is smaller or equal to 1, or between -1 and +1. If it is equal to 1, it's called this case of dilation bands. In other words, we have no shear displacement, only normal displacement, only volumetric displacement, only dilation. On the opposite, if it's -1, we have only normal displacement, but in the other direction. It's called compaction bands. This is the case of dilation bands, this is the case of compaction bands. And in between, we have shear bands, and these shear bands are either dilatant, this is observed, for example, at low confining pressure, or compactant, if at higher confining pressure. Okay, let's make now the link between various concepts. We have obtained the strain localization criterion as a singularity of the acoustic tensor. And we have, when we write the governing equation of a mechanical problem, a set of partial differential equations. And for this set of partial differential equations, we may ask the question of unicity. And as it is second order differential equation, we know that we discriminate between elliptic, or parabolic, or hyperbolic equation. For example, if we take elasticity, we can demonstrate that the equations are always elliptic, which is a good news, because it means that we have unicity, existence and unicity of the solutions. Now, if we look at the general strong ellipticity condition, what is it? It is that for any vector n, this is the mathematical definition, C, I, J, K, L, and J, and L is strictly definitely positive. So we recognize here exactly this tensor, which is the acoustic tensor. So if the acoustic tensor becomes singular, it means that we lose the condition of strong ellipticity. So it means that we lose the condition of uniqueness of the solution. This has important consequences because, for example, we are used to use numerical models based on finite element computer codes, and you know that the finite element method is appropriate to solve numerically elliptic equations. now we see that if we go post the localization state, in the post-localization state, we lose electricity. This is why we have problems when we use finite element cores, for example, with soldering behavior, and this undesirable situation manifest by the fact, for example, that we have mesh dependency of the result. This is why we need to regularize the equation. So what we have to remember now is that as soon as we go beyond the localization point, we have to be careful in the nature of the equations that we are solving and have the appropriate tools in terms of numerical modeling in particular. As the acoustic tensor, when it is strictly definite positive, it means that all the velocities of acceleration waves are real. So localization criterion corresponds to a state for which the velocity of the wave propagation in the direction normal to the band is zero. These are stationary waves. So you see we have this link on this deformation model. We have obtained that strain localization criterion is the singularity of the acoustic tensor. It corresponds to the loss of electricity of the governing equations, and it corresponds to the formation of stationary waves. So we can see an example of a constitutive model commonly used for rocks. We take here the Drucker elasticity model that you all know, but not necessarily linear. The friction and the dilatancy coefficient can depend upon the state of stress. This permits to describe exactly in the same way that we've seen in the previous talk of failure envelope that can incorporate both the brittle and the ductile part. So here we have the ductile part, and here we have the rather brittle part. So here it's frictional and dilatant, and here it's compacting, both coefficients are there. Okay, so if you look at the paper of Rudnick-Iran of NRS, you have the explicit condition in terms of the critical hardening modulus for which a strain localization is possible. You see, it depends on the friction and dilatancy. Again, we see that it doesn't depend only on one material property, for example, the friction. It depends also on the dilatancy, the condition of strain localization. Also, it depends, and you see, it's the ratio between the intermediate shear stress and tau and sigma. And so it depends also on the state of stress. It's not the same in triaxial test or in biaxial test, in plane strain. And we have also the orientation, which is not simply P over 4 plus P over 2. It's given here, this orientation, and you see again, it depends. We don't get the same orientation with different mode of loading. And now this paper was enhanced with a later work of Perrin and Leblond, who noticed that as we have X sign here, alpha, this is valid only if alpha is between -1 and 1. And from this point, they could deduce the condition for which we have dilation bands corresponding to an orientation of the band which is parallel to the axis of the sample, or the orientation of the band which is normal to the sample. This is compaction bands. Okay, so I go a little quickly now, but what we can remember for that, in the post-bifurcation regime, the governing equations becomes mathematically imposed. They lose uniqueness. You have to be careful in numerical modeling. In all this analysis, we could get the onset of localization, but we could not say anything about the thickness of the shear band. And this deficiency comes from the fact that we have no information about some material length characterized of the material. In other words, the extent of the plastically softening region is undetermined. So, in order to go a little further, we need continuum models with some information on the microstructures, because we have seen in the observation that, for example, the thickness of the shear band is very much controlled by some typical size of the grain. And this is possible by resorting to what is called generalized continuum theories, such as COSRA, higher grade continua. They contain a material length related to the smaller scale physics that will limit localization zone thickness and permits robust post-localization computations. It's important because, for example, if we look at the problem of rapid shake, like it occurs in seismic slip or in landslide, obviously the quantity of heat which is produced depends upon the thickness. And the thickness of the localization zone is not necessarily constant. It evolves in due course of the deformation process. So we need to have the proper tools in order to be able to capture the thickness and its evolution in relation with also the modification of the microstructure. Just to give you an example, this is for numerical applications. I think it's familiar for some of you. If we want to solve using finite element with some code, the problem of a layer that we share here, we have this typical mesh dependency depending on the number of elements that we take. If we take more elements, we have here the steeper post-peak response corresponding to a thinner shear band, because in numerical code, the thickness of the shear band is always one element, which is not, of course, satisfactory. Whereas if we have the proper tools of regularization here at COSRA, we see that in the post-peak we can ensure mesh independence. So now I would like to give you an example of work that has been done in due course of the PhD thesis of Youssouf Abdallah, also together with Michel Bonnet. And starting from the idea that we have seen also previously, that the microstructure of the material plays a major role in analyzing failure and localized failure load. And the idea here is to combine trial testing, X-ray computed tomography, in order to obtain 3D strain maps and porosity maps, and look in due course of the loading process how these quantities can be determined and how they evolve. The rock that was studied here is the Saint-Maximin limestone. This comes from a quarry in the north of Paris. It has been studied in many laboratories. It's a building stone, and here it has the advantage to have a very large porosity. So the transition between the ductile and brittle and ductile regime is obtained at rather low confining stress. So in the laboratory, it is quite easy to study the various regime. But as you know, the microstructure of limestones is generally much more complex than the one of sandstone. Also, acoustic emission techniques that are very efficient, as we have seen in the talk of Christian, very efficient for sandstone. They are not so efficient for carbonates. And this is why the use of microtomography to have access to the deformation field inside the sample is so useful. So if we look here at the micrograph of this rock, this is the scale, 300 microns, we distinguish the calcite grains, and you see that these calcite grains with a typical size between 150 and 300 microns, they are themselves porous. So we have microporosity, and we recognize here, you see it's a little darker. These are quartz grains. So we have mostly calcite, 80%, but we have also quartz grains. And we have also these shells. And we have macropores, we have mesopores, smaller, and we have micropores inside the calcite. Then these are typical size that one could determine for this maximum. So this is an X-ray image where we see in different gray level the different porosity, and that we can also compute. So blue is lower porosity and red is higher porosity. And you see we have this alternation of higher or lower porosity zones with a typical wavelength of about 1 centimeter. And so at various stages of loading, so here in these experiments, at the end of each stage, we have to unload and put the sample inside the tomograph and make this kind of images. The work is now continued together with Alexandre and Gaznat and Michel de Bornet in order to be able to make these images in due course of the loading. So this means that we have to put the cell in the map, in the map. Nevertheless, we have here in the first stage already these zones of strain localization, and in a second stage with higher deformation in boards, we have seen that the deformation bands have enlarged and they have also propagated. From the image and also from the determination of the strain field, we can go back to what we said before. What are the type of deformation bands that we obtain? Are they compaction bands? Are they shear bands? And for that, we do exactly what is written here, that we try to compute the eigenvectors, or we calculate this ratio, which takes value between 1 and -1. And if we have -1, we have pure compaction bands, and in between we have compacting or dilated shear bands. So we have, for example, deformation, and from the local displacement field, we can compute this product, scalar product, that we normalize with the displacement of the element. And this is what Yusuf Abdallah obtained from using this approach. You see we have different bands here with numbers 1, 2, 3, and so on. And you see that in the first yes, we see that at least for this deformation bands, the scalar product here is almost -1, very close to -1. So it means that we have compaction bands that are formed. But it's interesting to see that they are not necessarily horizontal. They would be horizontal if the material were homogeneous, which is not the case. We have the local heterogeneity of the material, which leads to local heterogeneity of the stress field. So for this type of heterogeneous material, the heterogeneity of the porosity is a main feature of the material. For this type of material, we can have, you see, compaction bands which are not necessarily horizontal. And we have also, but you see that the orientation is very different. Bands which are identified as compactive shear bands. It's interesting also to compare the volumetric strain map and the porosity map to evidence that, you see, the zones of high volumetric compaction corresponds to the zones of higher porosity. So in this rock, the heterogeneity of the porosity is controlling the deformation. Also, you see, we have here two poles, this one and this one. This is in the denser region, this is in the more porous one, and in due course of the deformation process, you see that this pole, which is in the more porous zone, will collapse, and the other is still intact. So this indicates that a material point in this sample will behave differently whether it is in the porous zone or a more denser zone. This is why we are now looking more in detail in the mechanisms, deformation mechanisms, specifically on these zones and on these ones. But this is exactly the concept of non-local behavior of the material element. That the behavior of a material point depends upon the properties of a small volume around this material. And this is why, in the modeling now, we will resort to concept of non-locality or gradient model or higher order continuum modeling. And this is how it is done. In classical, or what we call Cauchy continuum, what we use commonly, we consider an assembly of material points for which we can define kinematics, which is the displacement of each material point. Now, with a generalized continuum, to each material point, we associate a micro volume around this point, and we will describe not only the displacement of the material point, but also the deformation of the micro volume which is attached to the material point. So you understand that we have concepts of macro displacement, but also concepts of micro displacement. How in this micro volume, how the point x prime is moving as compared to the point x in the deformed configuration. And we can derive very rigorously all the theory. And, although this type of theory can be traced back to the end of 19th century or also to the 60s, there was very important work done especially by Midi. There is, for those of you who are interested, a very clear paper and very rigorous paper by Germain. And the derivation are done by writing the power density of internal forces, which in classical continuum theories depends only on this term, but here we have the higher order terms, because it depends not only on the deformation or the displacement of the material point, but also on the micro displacement. So the deformation at the micro scale also intervene in the global computation of the deformation energy of the system. Okay? For this, I will not go too much into detail, but as we are from the observation, we have seen that the important feature is the compaction. It's a volumetric deformation. So we use here a restricted higher order continuum for which we look just as an additional quantity, the volumetric quantities not the shear quantities. Of course, we can make things more complicated, but this was enough. In other words, what we are interested in is not only the displacement, but also not only the volumetric deformation, but also its higher gradients. Okay, I try not to give too many equations, but just that you see the general frame. The yield surface now depends not only on the stresses, but also on the higher order stresses. And as a consequence, when we write the constitutive equation, rate constitutive equations, we have some additional terms here. And we can make a correspondence also between this approach and the second gradient plasticity, where you see the hardening parameters are not only the accumulated volumetric plastic strain, but also its second gradient. But now, if we go to these theories and we introduce these additional quantities, the key question is now, how can we calibrate the additional constitutive parameters? And this is where it's very useful to have this local analysis of the displacement field, because through the images that we have done on the macrotomograph and the evolution of the various quantities, we can calibrate on these fields the additional quantities that we need. Another way that was done when we were not able to have this detailed information at the local scale was to look, for example, at the thickness of the bands, and through the analysis back analyze the appropriate constitutive parameters, additional constitutive parameters that could be compatible with the observed thickness of the band. But this is much more robust. Okay, so what is the calibration strategy? First, we have to calibrate the standard elastoplastic components of the Cauchy, and this is done by using the stresses curve, and this is the type of failure envelope that we have, and how it is it can harden. We have to, in this model, determine what is the material length of this model. In other words, what is the size of the macro volume that we have to consider attached to each material length. And this, there is not a unique choice. It's a matter of taste, I would say. We have to look at some periodic scale, and we can choose the one we like. The simplest is the best. But if we choose a different material length or different unit cell, we get different model. So here we make the choice that the material length is given by the characteristic length scale of the porosity interactivity. Visually, we have seen that it's the order of 1 centimeter, because this is the scale of the alternation between more porous and less porous zones. Now we have to calibrate the hardening laws, and the hardening laws depend not only on the accumulated plastic strain but on its second gradient. But as we have the full field of displacement inside the sample, we can compute also the gradient of displacement and the gradient of deformation. And we have some also higher order modulus that we have to calibrate, and this is done, I will show you immediately, through stability analysis, linear stability analysis. So you see how we do. We have porosity maps, and we, to give you an image, imagine the alternation of zones of higher porosity or lower porosity, and this is the typical unit cell that we are searching. So through a Fourier transform of the porosity profile, we can obtain the first dominant wavelength, which is here, you see, of the order of 2.4 centimeters. Just to show you how we use this porosity map to compute not only the average porosity, but also its gradient inside each image, inside, and just making a Taylor development at the second order. You see that in any sample, we can compute these quantities. So from these quantities, we can calibrate the hardening loads. Now, let me go back a little bit. There is one, there is one additional parameter here, which relates the higher order stress and the higher order strain gradient. And we can see in the analysis of the stability that this parameter is important in controlling the condition from localization. Namely, this parameter is important in the boundary between compactive shear bands and compaction bands. So, what we do is a linear stability analysis. I have to say something. We have seen the deformation band model, for which we have obtained that the condition of localization is the singularity of the acoustic tensor. This is fine for dry material and for homogeneous material. Now we see that we go into detail in a material with microstructure, or in the next step we put some water in the system or temperature, and for that we have to resort to rather linear stability analysis, or enough stability in that sense that we perturb the system and we look for the evolution in time of the perturbation. This is exactly what we do. We have an equilibrium state that we perturb, and its evolution in time is decomposed in Fourier modes. In space is decomposed in Fourier modes, and the time is of exponential form. So you see, if we look at the evolution in time of the perturbation, if S is negative, it means that it vanishes in time. If S is positive, it means that it explodes in time. So the condition for instability is S positive. Governing equation, momentum balance, constitutive equation. At the end, what we obtain is this equation that for which the unknown is here. You see the growth rate of instability, and we look for possibility of negative values. And what I want to show to you is that we obtain conditions of instability, and we obtain the boundary between compacting shear bands and compaction bands here that depend very much on this parameter. And in the experiments, it was observed that all experiments below 9 megapascal corresponds to the formation of shear bands, whereas above 9 megapascal, it was corresponding to compaction bands. So this is how we calibrate this parameter E, so that the boundary corresponds to this confining stress. Okay, so this is just a summary. The stress strain measurements, the Cauchy component, porosity map to have the internal neck, the hardening laws through the porosity maps, and linear stability analysis to have the higher order. So we have, of course, to see this more in detail, but the general idea is that now we can calibrate fully this type of constitutive model. And so once we have a constitutive model, we can put it in a finite element road. And because we have the good ingredients of gradient model, we do not have problem of mesh dependency. The computations are robust and independent of the mesh. And you see in due course of imposed axial load, axial deformation, how the plastic axial strain is localized. And this corresponds to the deformation fields at various levels of deformation. So what we observed in this computation is that it's formed in the central zone, and it's enlarged in due course of the loading. And the band becomes larger. And we can compare the computations at various stages of loading, here only two. In terms of the thickness, you see that the thickness is increasing in due course of the loading, and also the onset, the deformation and inside the band, with good correspondence between observations and the mode. So this is an example how the microstructure and its heterogeneity influences the formation of this type of deformation. So, we summarize. We have a key role of porosity heterogeneity for the onset and propagation of compaction bands, the non-local character of the deformation process, and gradient plasticity constitutive model that can be fully calibrated from triaxial data combined with imaging techniques. Now, I would like to go further and introduce some couplings. And first, hydromechanical coupling. We know that in fluid saturated rocks, the time scale of the formation process has to be compared to the characteristic diffusion time in order to assess what could be the induced pore pressure change. So in drain boundary conditions, and if the deformation process is slow enough, the pore pressure remains constant, and any alterations is equilibrated by the pore fluid flow. Under undrained boundary conditions, or if the deformation occurs very rapidly, like in the case, for example, for gravitational slip or seismic slip, then pore pressure changes occur and persist and modify the effective stress and consequently the strength of the material. Now, we have also to take attention to the type of regime. In the brittle regime, rocks tend to dilate, whereas in the ductile regime, they tend to contract. So, any elastic volume changes will cause a change in the pore pressure. So, dilation or contractions of the rocks is the key mechanisms to cause the coupling between inelastic deformation and pore fluid flow. So, in the following, we will analyze how dilatant behavior or compacting behavior leads to different types of instability. First, I would like to present a general result, and then we go with an example. Now we have a rock or porous media which is saturated with a fluid, and we have to write constitutive equations. And as we have now two phases, a solid phase and a fluid, constitutive equations can be written in two equivalent ways. Either using the drain constitutive tensor, and we have that the rate of stress depends on the rate of strain and also the rate of pore pressure, or use the undrained tangent modulus and write the change of the rate of stress depending also on the change on the rate of the fluid mass component. We have the governing equation. So in addition to the momentum balance, we have also the fluid mass balance and also the Darcy law, which relates the flux to the pore pressure vector. This is I believe familiar to all of you. Now, to study localization, again, we have to perform a linear stability analysis. We cannot use directly the deformation band model that I've shown before. The good technique is to use this perturbation. So we have to perturb all the set of fields. X is the displacement, the stresses, the pore pressure, or we have temperature, also we have to do. So this is the perturbation of delta X of the field X. Again, we decompose it Fourier modes. C is the wave number. plus ST, the evolution of time, is of exponential form, and we look at the possibility of having positive value, or these positive real values for S. At the end, what we obtain is the following. So the unknown is S. So for X, for each particular perturbation mode, so X particular value of the wave number or of the wavelength, we compute the corresponding growth coefficient S. So we have to solve this equation. It's very simple. And we have to look at the change of sign of S when it is negative and when it becomes positive. And you see that change of sign of S is linked to the change of sign of the numerator or the change of sign of the denominator. What we recognize here, you see this is the acoustic tensor of the drain behavior. And this is the acoustic tensor of the undrained behavior. So in other words, instability is possible either if the drain acoustic tensor or the undrained acoustic tensor, independently of the true loading process, whether we are drain or undrained, independently of that or in between, what we have to check if the undrained or the drain acoustic tensor become singular. And in some cases, one is becoming singular before the other. This is what we are going to see. So, tranquilization occurs when the drain or the undrained acoustic tensor becomes singular. You can find the details in a very interesting work of Ahmad Belalal and Claudia Pomi in the early 2000s. So, in summary, the two conditions must be checked on the real deformation path, which is not necessarily drained or undrained, to infer which one is first met. Now, what we can demonstrate for associative behavior, it is shown that the singularity of the drain acoustic tensor occurs before the singularity of the undrained acoustic tensor, which means that the instability occurs when the condition for localization of the underlying drain deformation is met. So for associative plasticity, we have to check the conditions for drain behavior. For non-associative behavior, instability is controlled either by the drain or the undrained properties, depending on the constitutive equations and on the loading path. And what we can show, and we'll see the example just after, is that when for highly porous rock we have a compacted behavior, the conditions of localization for undrained response can be met before the drain response. Okay, so let's see this example. The same layer as in the beginning of the talk, but now we have a fluid saturated material. And this problem has been addressed by Palmer and Heiss in a very important paper on dilatant hardening behavior in 1975, and also Bartoulakis in two papers, and later with Uniki, Karagash, and Belalal. So we have, again, a uniform state of stress, but now we have also to consider the mass balance equations for the fluid. Here, in order to make things simple, we consider that the grains, also solid phase, and the fluid are incompressible. And if you are interested in the more general case, for which the fluid and the grains are compressible, as is the case for rocks, then in the appendix of the paper of Heiss, you have the derivations. But formally, it's exactly the same, just maybe the numerical values are a bit changed. So again, we have the constitutive equations as before, but now you see that they are written in terms of the effective Terzaghi stress or increment of stress, and we have also to consider the plastic volumetric behavior. Beta is the dilatancy coefficient. Okay, so for the homogeneous strain response, we are first interested in the homogeneous response. If it is draining, we have no change in the pore pressure, and we obtain immediately, it's exactly as for the as for the dry case, the relation between the increment of stress and the increment of shear strain with this plastic modulus H. Whereas if we consider now the undrained response, for which the volumetric deformation is 0, then we have, you see, a different tangent modulus, which depends not only on H and G, but also on beta and mu. And N is the bulk modulus in plane strain. So if we draw this response, this is the drain response or the dry response. If we have a material which is dilating beta positive, you see that this slope is bigger than this one. So we are above. In other words, for dilating undrained behavior, we have dilatant hardening, material hardens. If we have, on the other hand, beta negative, contracting material, this slope is smaller than this one. So this curve is below the other one. Okay. So let's do the analysis. We have a layer, and we assume that we prevent any flux at the boundaries. So the flux is 0. This means that the boundaries are impervious, or that we have undrained boundary conditions. We have homogeneous solution up to some state, and we look again at the perturbation. So we perturb all the fields, and again the same technique. We decompose all the perturbation fields in Fourier modes. So for each wavelength of the perturbation, we compute the growth in time coefficient S. And this is what we obtain. This is the solution. S, how it depends upon the wavelength, the material parameter, mu, beta, and kappa is diffusivity. So we see that if these quantities K and are positive, and this square of obviously is positive, so you see that the sign, if this quantity is negative, then S becomes positive. What is this quantity? It is exactly the drain modulus. So past peak of the drain response, S becomes positive. If we write here the diffusion equation, you see that C, which is related to this quantity, it means that the diffusion coefficient becomes negative. We are not used to diffusion coefficients which are negative. It means that the time is running backwards. Or in other words, if we have non-uniformities, if you have positive diffusion, they vanish. In that case, if you have negative diffusivity, if you have non-uniformities, they become more and more localized in time, not more diffuse. So if we have some more pressure perturbation, they will explode, they will not vanish. Okay, so for dilatant material, instability occurs at the peak here of the drain of the drain response, so when H equals 0, when the underlying drain response passes through the peak. For compacting materials, the denominator yes, for here I've seen the analysis for the dilatant behavior. For the compacting behavior, you see that the denominator, because beta is negative, can go through 0 at some point. And so the denominator can change sign before the numerator. This would be this case. So, what is the consequence of that? We see that in one case, S becomes S depends upon lambda, and S becomes bigger if lambda is smaller. So the perturbation with the smaller wavelength propagates faster. In other words, everything localized in a zone of infinitely small thickness. Now, for the other case, if this denominator goes to 0, it means that S goes to infinity. The perturbation rate is infinite for all wavelengths. Okay? So this is a sign of two deficiencies, impulseness and the lack of material length. And this has to be regularized by putting some additional physics in the system. What we are missing, okay, we have the condition, and this is true. We have the condition for instability. So for undrained dilatant material, it occurs there. For undrained contractile material, it occurs there. And for drained material, it occurs there. But how does it occur? We have to put some more physics in that. We need to regularize, consider inertia, rate dependency, or microstructure, or all together. Okay? So I will just give you an example of how we can incorporate rate dependency by writing a yield condition that depends not only on the accumulated plastic strain, but on the plastic strain rate. And this is this kind of friction laws that depend upon the strain rate is also very much used. It's known as radiant state friction laws, especially in seismology. So now we have some additional hardening modulus here, delta, you see, which is how the strength is changing with change of the plastic strain rate. Okay, and at the end of the computation, this is what we get. Condition for positive growth of the instability is when this quantity is equal to, becomes negative. So we see that it occurs first for the larger value of lambda. Now, not the smaller as we had before, but the larger one. What is the largest wavelength? It is the thickness of the layer. So it means that diffuse instability occurs first for undrained sharing of compacting materials. So we have here the stability conditions, and looking at the expression here, we recognize that the diffusivity and the rate dependency, they are both in the numerator. It means that the strain rate sensitivity is amplified by the porphyry diffusion to delay instability. So if we have more strain rate sensitivity, if we have a more higher permeability, so more diffusion, all this delay the instability. Or in other words, if we have very low permeability, then we have instability which occurs early. We see that the sharing rate is in the denominator, so high sharing rate leads to earlier instability. And if the layer thickness is small enough, then diffuse instability may be prevented and localized instability will occur first. So we have here an example for which we see the combination of, because diffusion is a time-dependent process, in order to study stability, the necessity to account also for rate dependency of the material properties. Okay, so I have maybe just 10 more minutes, and yes, first I summarize hydromechanical coupling and instability. For associated behavior, instability occurs when the condition of localization of the underlying drain deformation is met. For non-associative behavior, instability is controlled by the drain or drain properties. And for compactant behavior, undrained response can induce instability before the drain response. And maybe in the last 10 minutes, I will just choose one topic, which is chemically induced compaction bending. One could look also on thermal hydromechanical couplings or grain crushing, but we don't have time for that. So I would like to address a problem very similar to what was presented in the first talk, the problem of diffusion of reactive fluid dissolution and how this can enhance instability in terms of localized deformation. So the conceptual model that we have in mind is the following. We have some flow of a reactive fluid which weakens the material, and this is causing grain crushing or damage. Grain crushing induces an increase of the effective specific area of the grains or of the soil, so that you have a larger surface of interaction between the flowing fluid and the grains. So if we have damage and grains which are crushed, any dissolution process will be more efficient and will occur faster. So we see that if we have faster dissolution, then we have faster softening, and we have here a positive loop for which we can ask about the possible instability. When we are looking for this type of interaction, a chemical interaction, such as dissolution, we have to distinguish between different scales. What we write at the macro scale, or the representative elementary volume, is the constitutive behavior, momentum balance, mass balance of the fluid, of the solid, and so on. This is written at the macro scale. But some other phenomena has to be considered as a smaller scale, as the scale of the grains. So you see very schematically, I represent here the representative volume as an assembly of grains, and the grains are, you see, with different level of grain, just indicating that it's not necessarily homogeneous. So at the small scale, what we have to write is the kinetics of the dissolution. It depends on the grain size, and also all grain crushing, solid skeleton, micro cracking. These are phenomena that occurs at the scale smaller than the representative elementary volume. Let's consider some dissolution, chemical dissolution equation, the solid and solvent, which give the solution, quartz or carbonate, and we write the reaction rate of this chemical reaction. W2 is a mass fraction of the dissolution product. Here it's one other equation, and you see that it depends upon S, which is a specific area of the grains. E is the void ratio, we can use also the porosity, and the specific area of the grain is inversely proportional to the grain size. Now we have to introduce an evolution of the grain size because of the damage process. Of course, we can here resort to some advanced breakage mechanics, as done by my colleague Italianard. Here we use a very simple law that was proposed by Paul Lard, that you see the evolution of the grain size depends upon the energy that we give to the system, the mechanical energy that we give to the system. So it's very related to the level of stress. And we have only one parameter here, which is A, a grain crushability. And we write this equation proposed by Lab in terms of the evolution of the specific area. You see, a very, very simple equation. So now we have to upscale, and especially upscale the dissolution process. So we have to write what is happening here at the grain scale and average it on the size of the REV. So we need to introduce the size of the REV that I call L. And when I make this averaging of the mass fraction of the dissolution product over the REV, I just make a second order Taylor development to obtain, you see, this kind of non-local or gradient evolution, which introduces a characteristic length, chemical length, you see, related to the size of the REV. What is the size of the REV? It is a unit cell which is sufficiently big to be used as a periodic cell for the whole region, so that contains enough information about the locality regions. So this depends on the material, and this is a choice that we have to do. Okay, so as we have seen in the experiment of Christian, we have here a failure surface, a yield surface that can evolve in due course of increasing porosity, and porosity increases because of the chemical reaction progress. So this is how we have the coupling between the mechanics and the chemistry. Okay, and as we have here the non-local evolution of the dissolution product, we can deduce exactly the evolution of the chemical reaction products. So you see that we have here a non-local competitive law, which doesn't come directly from the mechanics. Here it comes only from the chemistry of the problem. Of course, we can do more complex things and combine different high-order models. So just to give you an example, more qualitative, this is the modeling window of a reservoir with carbonate grain store with some properties, typical properties, and some value. And it's more to show you qualitatively the effect of each parameter. So what do we have? This is the initial state. Then we are under odometric condition, 1D problem. We inject fluid. The system deforms homogeneously from A to B. B, we enter in this zone that has been computed before as a zone of possible localization, possible instability. And the system evolves from B to C, the final state, in a more localized manner. This is what you observe here. So this is in due time, you have seen that we have homogeneous deformation and at some point localized deformation. Again, this is point A, point B, and at the end point C. And this is induced by the coupling between the dissolution and the softening of the material. So in terms of deformation, this is what is occurring far from the. This is the localized zone here, the peak here. This is far from, you have very small deformation, and this is an average. Okay, so now if we look at some sensitivity analysis, what we observe is with this type of curve, is the growth coefficient at instability as a function of the wavelength of the instability mode. It means that the less permeable the medium is, the more localized the compaction instability is. You see, we have for a smaller wavelength an instability that propagates faster. So if the medium is also very low permeability, then we have an instability that grows faster. we can do the same thing. It's a type of sensitivity analysis looking at the crushability condition. And what we obtain, this is the dominant wavelength of the instability or the shear band thickness, it's related to that. If the grains are more crushable, if the grains are less crushable, then the dominant wavelength is growing, tending to infinity, which means that the deformation is not localized. On the other hand, if the grains are very crushable, then lambda is finite and small, so deformation is more localized. And also here the effect of permeability, if the reaction is faster, the narrower, if the, this is not the reaction, if the permeability is smaller, then we have more localized, and if the reaction is faster, the compaction zone is also narrow. So in summary, chemically, combined effect of dissolution and grain crushing can give a positive feedback. It's a multi-scale process, and the heterogeneity of the dissolution process controls the spacing and the thickness of the compaction. Okay, I believe I had to stop, so I will go to my conclusions. I hope that you're convinced that the localization process is non-local and multi-scale character. Nowadays, advanced laboratory testing permits to have quantitative analysis of trend localization phenomena and calibration of high-order constitutive models. We have seen the importance of multiphysics and coupled processes, and we can develop robust numerical tools by considering the microstructure of the material, and of course there are many other challenging issues for the young PhD students to attack. Thank you.
Thank you very much, Jean, for this very detailed analysis of localization phenomena and stability. Well, there's room for questions.
I have several questions, but one of them is you emphasize the role of the microscale in the organization of the organization. And you assess this microscale in two ways compared when you look at the first case in your experiment with the topographic measurements, you were mapping the porosity to assess this length scale. And in the second case, you look at the dissolution effect. My question is, how can you check that's the dominant parameter to control this intrinsic length scale? And do you have some argument for saying that mapping the porosity is the best way to assess it? And since it's a different strategy when you have other type of reaction. And what I have in mind is if you would have to upscale this analysis to the field scale, for instance, how would you proceed to assess this interesting scale?
Yes, good, thank you. So the first point is we have seen when you do strain localization analysis, at some point we're interested to what is occurring at a small scale. We have seen that the shear band is not a geotechnical structure, everything occurs in a few grains. So obviously, if we have some homogenization technique that we have used to have appropriate constitutive laws for a large sample or structure, then we have now to go back to what is happening at the grain scale. So first observation from standard experiments on soil or rocks, the importance of the microstructure. Also, we have seen from, I would say, a numerical point of view, practical point of view, a mathematical point of view, the analysis is okay just to have the concept of localization, but fails to go beyond. So we need some additional tools, and one could use viscoplasticity or some purely mathematical tools. So the idea is to try to go more in the physics of the problem, and this is the question: what is the appropriate physics that control for different types of problems, the post-peak of the localization. So exactly in the first examples I've shown, because of the observation, we have seen that the positive heterogeneity was a key factor that controls. We went into a model that would account for the positive heterogeneity. In fact, if we look, the second approach is not so different. It's the same ideas, because it's the heterogeneity of the dissolution process, which is linked to the grain size. Grain size is linked also to the heterogeneity of the porosity. So basically, physically, it's the same idea. The heterogeneity of the process at the lower scale that we try to capture. We could probably get the same result by considering the heterogeneity of the porosity, and then from the porosity go to the specific surface and have the heterogeneity of the. So this is for the choice of the analysis. We could look at a different phenomenon, which is sharing in the evolution of the grain size distribution and its effect on the further localization process. Now, the second question is how we can scale this problem. This is why exactly we are working together with Michel and Alexandre on trying to understand further the deformation mechanism at very low, at a lower scale than what we have observed here, which is the sample scale. And we are making some experiments of the more porous or less porous, just to understand how what occurs at the smaller scale control what happens at the scale of the sample. And from that, try maybe to have some inspiration now to go in the next scale. Intuitively, what we can say, imagine that now at the scale of the reservoir we have some logs of the porosity or some other measurements that would relate to the porosity, and you find some dominant wavelength of that. This wavelength will give you, from this type of analysis, typically the spacing and the thickness of the compaction bands that would occur in some loading or depleting process. This is the idea behind that. But at the moment, so we are exploring one scale below in order to go from the very small scale to the mesoscale.
So, Sean, also about the last part of the topic, the role of distribution and localization. So, do you think this implies, for example, that in impure sandstones, where you have what are effectively styloids developed, do you think that this mechanism is responsible for those? I think it could be.
Localized, yes, localized dissolution processes through weaker or through weaker zones.
Yeah, so if you would have grain size reduction due to grit processes that you put in this model, and that enhances dissolution, then you would, if you have an impure sandstone, you'd accumulate insoluble material there, which would of course further influence the flow pattern from that point on. But that actually seems to me like a very likely explanation for these types of periodic structures that you see in impure sandstones.
Yes, yes, I believe. Yeah, could be. Because this is always asking the question, what controls the periodicity of these beautiful structures that we observe in nature?
Yes. Yeah, thanks.
Yeah, thank you. Anna?
Yes. In this test on carbonates, did you verify if the sample size actually can be considered ARV? Did you do tests to see if the statistical indicators of the porosity remain unchanged for this side or something like this?
Yes, this is a very good point, because you see that when we have the typical sample of 40 millimeters, and that we have an alternation of about 1 or 2 centimeters between these two zones. The question is whether the sample is maybe too small to be representative. So this is why my interpretation is to see this sample as a unit cell that contains, and when we do the analysis of the images, we take a unit cell that contains one zone of, for example, one central zone of more porous, and which is surrounded with a zone of less porous material. So we work at the scale of this kind of chest plate analogy. But really it's a very simplistic model, I agree. And we see now with the experiments at a smaller scale that the processes, especially in what appears in the dense zone, the material is heterogeneous at a lower scale. And this is what we are analyzing at the moment.
Yes, sure, that's it. Thank you very much. Do you think this kind of analysis, the strain localization analysis, should enter the engineering work?
Should enter, sorry?
To the engineering work?
I believe yes, and I believe they do. When people are looking for example, on borehole stability or sand production and these kind of things, localized pattern of failure is important. And as we have seen that we need robust model in the post-failure analysis. I believe maybe it's not very common, but some advanced engineering studies take into account.
I have a little question or remark. So several times we came to the point that there is some differences between the sandstone, which microstructure is very simple, and the complexity of the carbonates. And specifically with regard to this chemical coupling processes, but I have this remark that the solubility of calcite or silicon dioxide depend on temperature, and in one case solubility increases with temperature, so this is for silicon, while it decreases for calcite. So I have just this remark that this thermal aspect on the dissolution kinetics might be very important and probably explain some differences between these two types of major reservoir rocks.
To consider the effect of temperature.
The effect of the temperature on the solubility and therefore kinetics. So do you would also okay, you mentioned it. I have no time to go into this detail, but do you refine the models with respect to the temperature dependence?
Yeah, we have not done this coupling the chemistry and temperature. Oh, although not in this application, I've done it in some other work for which I was looking at the seismic slip and combining therefore the effect of high temperature with dehydration or decarbonation reactions, and again looking at the evolution of the localization. But it's a different problem as
yes,
because the kinetics depend on you have to reach some pressure.
Thank you.
Okay, thank you.
Invitation. My presentation, I think, will be mostly at another scale from what we heard this morning. I will try to introduce some features of deep geothermal energy, and in particular what I call EGS, if I will define that, and some connections with one of the major risks attached to it, as you may know, which is induced seismicity. And I will rely on some of the mechanical mechanisms that were introduced this morning, and possibly the talk after from Brice will also complement that. So the outline I would like to follow is the following. I would like to split the presentation in three parts. Basically, one, to introduce the deep geothermal energy, the EGS concept I will focus on, and this strategy for heat mining, and the related seismicity that is attached to it. And then I would like to introduce two case studies. One famous one, which is one of the oldest one we have in Europe, which is the Sulzufere case. And I would like to show that it's still first a very active scientific research on it, even if it's quite old data sets, but still very interesting. And the other extreme, which is the very recent case, which is the case of Vendenheim, so the Strasbourg case, where the company Fonroche, now more recently Geo-Energy, tried to develop such a project in Alsace, and faced a major issue that led to the stop of the project. So this is the kind of the program, and I will try to split that in three parts, as I said, and follow this general introduction. So just to start with, what is deep geothermal energy, in particular the EGS one? I just start from a very famous figure that I guess all of you know. For as soon as you have interest in deep geothermal energy, you find this picture produced by the BRGM some years back. But it introduced nicely the different concept and the different type of resources. So I think there are two ingredients or two key points to look at: is the resource and the use in this. And there is some link between the two, but not always. Yeah. So in terms of resources, there are aquifers, very shallow aquifers that are at, let's say, 20 degrees, 40 degrees, and that are for basically use attached to a heat pump. And this will not the focus of my presentation. And there is also a focus, another type of geothermal energy, which is for direct use. So search for aquifer where the water is basically at the temperature you're going to use it, and typically for heating this is 80 degrees. So that's now part of the deep geothermal energy. This is a recent trend, but because it's mostly dominated by geological approaches or conditions and knowledge, but this is not also the part I'm going to focus on. And to continue on the part I'm not going to focus on is the right part, which is also something people have quickly in mind when they are dealing with deep geothermal energy, which is the one attached to volcanic area where heat can be very shallow. You can reach 250 in this example. The number is small, but it's here at a few hundred meter depths. And this is high energy or high enthalpy or high temperature geothermal energy. And I will not focus on that also. So my presentation will be in this intermediate case where we might have some temperature, let's say 200 degrees, but at a depth that is about 4 to 5 kilometers, or at least more than 3, let's say, or 2.5 kilometers. So the resources of interest here is that case, not too hot, quite deep, and most of the case related to faulting. But we will come back to that in a second. Just to complement the figure before about the use, so there are the different use. This graph is focusing on the use. So the low temperature is for heat pump, as I mentioned, shallow resources. There is direct use for heating and district heating and possibly some processes that require some heat. And typically, it is deep geothermal energy is attached to electricity production, but the trend is changing, I think, and more and more deep geothermal energy is also emphasizing on the heat, the use of heat, and more on the combination of heat and electricity. And as you will see later, there is still an evolution, a strong evolution, that it's not only heat, not only electricity, but also some minerals, and one of them is the lithium. And geothermal lithium is really boosting the domain, the sector recently. Okay, so the use is changing. The use is not so much linked to the resource nowadays. And this is why sometimes there is some sort of confusion in the terms of deep geothermal energy, and why I wanted just to phrase it a little bit to be more precise. This energy, as it is the focus of this workshop, is something that is developing very much. So this is one of the use I mentioned, the heat or cooling, but mostly heating, is evolving very strongly over the last years. And as a use for heating or cooling, this is from a recent report from IGA, this is evolving very fast, but heating is dominated by the development of heat pump. And so this is very shallow geothermal energy, and you have numbers for the different part of the world who are producing that. You see the typical values of this is a few tenths of gigawatt thermal that is installed, and it can be compared to the power energy, the nuclear power energy we have in France, which is of the order for one nuclear power plant about 1 gigawatt of energy that is produced. Yeah. So it's still it is still small, but it is becoming more and more important, and a strong development. But for heating, as I just mentioned, it is mostly dominated by heat pump and not so much related to the knowledge of the underground. What is more depending on the underground knowledge is electricity production, and this is about the similar world map. And first comment is to see the numbers, the order of magnitudes. They are typically 10 times smaller for each main part of the world. So it's significantly less production of energy. It's about those quantities. And the rise is also important, but not so important as the first one. And it's, you see, when they published this map, I think it's interesting that quickly they superimpose the red zones, which are the zones from the tectonic, the general tectonic plate and the general structure of the crust are the zone where the heat flux is important. Yeah. So these are the red zones where this high temperature geothermal energy I mentioned is very much developed, and this is where most of the electricity is produced nowadays. And there is a good match between the black dots, which are the important plants and production zone, and this distribution of the of the high temperature domain related to the tectonic plate dynamics. And there are a few points here at the center, a few black points that are basically out of the red domain. And this is what I will discuss here. This is the domain of research, is how to produce electricity, so sort of high efficiency geothermal energy, but outside the domain that are most favorable, the red domain that are the ones that are most favorable. And those sites, they are mostly in Europe. And this is where is the challenge, is how to produce electricity, so basically a lot of energy away from the optimal condition, I would say. And then I come back to my figure here of this domain of what I call EGS, this domain where it's not so favorable. You have to go quite deep. The circulation of the fluid, if it's necessary, might be modified. So you have to introduce a modification of the underground, which is typically not the case when you have high energy context. So you have to help the system to be favorable for this, and you have to deal with a deep system, not so easy to manage. And this is where the challenge is, and where the concept of EGS enter, and where it has to be also better defined, because there are different strategies for that. And I'm trying to explain these strategies here in a very simple way, or crude way, I would say. So, as I said, we are trying to, this in deep geothermal energy, one is trying to produce energy from a domain where there are typically previous tectonics, faults, fluids, material like this. This is the typical ingredients that you're needing, and typically the conditions for producing a lot of energy are not favorable, so you need to develop that. And there is two different ways of looking at that, or two different strategies that has been tried, developed, or reconsidered. I will comment on that. One is to say, okay, let's see how we do in high temperature geothermal energy, and basically we will try to go at the frontiers of that, in the ideas of saying my problem is a kind of optimization problem. I'm at the boundary of what I can do, so if I have a good knowledge of my natural material, if I have extremely good knowledge, I will be able to optimize it and make it feasible. So the fundamental strategy is to explore the medium at best and adjust the exploitation to the best knowledge of the natural material. And it looks simple when you do it this way, but it's very fundamental, because the strategy in optimizing it and developing it will be mostly relying on the exploration, because you will need to characterize your medium at best. And this is very demanding, especially if you are quite deep. To have a very good knowledge of your system, of your reservoir at 4 kilometer depth is difficult, costly, and it relies on a good knowledge of typically the fluid content, which is extremely difficult to know remotely from the surface. And it's also to have a knowledge of the natural conduit, because you aim at relying on the natural conduit, and the main natural conduits are faults. So a good knowledge of the fault status at depth is a challenging problem, especially to know if they are highly permeable, and this is difficult, and to know the fluid content that they have is a very challenging issue. And also because you are in a system that is poorly economical feasible, you want to optimize your exploitation and your exploration. And this is what is typically done is that projects don't have exploration wells, so exploration drilling to have a good knowledge. And this has immediately a strong impact on the risk. And I think the Strasbourg case is a very good example of that. Anyway, I was quite long on that part, which is the idea of enhancing the natural system. And this is what I call what are called the enhanced geothermal system. It is the typical name behind this EGS. It looks a little bit semantic, but I think there is a fundamental assumptions behind this, is that you will slightly modify your system, the less possible. And this, again, is an enhancement issue. The other strategy is very different, and is to say natural system is very difficult to know at best and to know sufficiently to be very precise and so on. So let's make a strategy that is as independent as possible of the natural medium and find sort of an engineering, what I call an engineered geothermal system, also EGS, but with a very different logic behind it is that, and this was a graph from the very first deep hydrothermal, deep EGS system, where you do see that the representation at depth is extremely simplified. It's an homogeneous material, and the project will basically design at ex nihilo all the exchanger, all the fractures, completely independently of the knowledge of the geological structure. So the strategy there is to be very invasive, kind of very to put a lot of effort in modifying the natural system to be effective in producing fluids or hot fluids. So the strategy is very different actually. One is let's know the minimum I need to provide such a project, and I will design massively my heat exchanger. The other one is I want to know at best the natural one, and I will optimize from that one. And the history of EGS is a really ping pong vision between these two, as we can see. Anyway, so this one, the engineered one, I will not discuss it so much because we have very little example of that, at least in particular in France, because this is relying a lot on fracking, and this fracking strategy is not possible in France. So there are a few initiatives over the world. I know two of them. The one is an American one, the ongoing Forge project that maybe some of you know, which is exactly trying to design a system with two wells. That is a strategy that is coming from the oil industry. Two side wells, and it will be introduced some connectors, typically shear fractures that will connect the two and make the system quite independent of the general geological context. It's a very interesting case, the Forge project, because it's a few hundred meters from a classical geothermal plant, which is relying on a hydrothermal system in a fractured material. So the opposite strategy I was mentioning are existing. The engineered one and the enhanced one are really existing at a few hundred meters away, which is a very unique case. So this project is ongoing, and the strategy, the way they do this is they did a first well. They are doing some hydraulic stimulation of that one, and now they are presently drilling the second well to go through this one and build the heat exchanger and start the test of this. And this idea is going to be developed shortly in Switzerland, in Lausanne, with the same concept, trying to build 2 wells with a set of fractures that will be the heat exchanger. And they will try to build a large surface exchange comparable to what has done before, which is more relying on either the pre-existing set of fractures or some newly introduced fractures. And this is very recent, ongoing, modern, basically the future of this technology. And in between was the SULEM project I mentioned, and it's quite interesting when you go back into the history of the SULEM project and basically the first reports in the 90s, and you see that this idea was basically already existing, such a sketch of 2 wells and developing fracturing in between, but was abandoned for the reason I will try to sum up in a second. And now we are coming back to this idea and exploring that there is a lot of completion issue in terms of wells and also possibility to control large hydro-shear fractures, which is a very important challenge. This is many questions about that. I mean, developments about that. So now I will go back to what I call the enhance EGS. So this idea that let's take the best of the natural system, and natural system where fluid exists and where heat might be accessible are these systems like the Rhine Graben, where you do have a large set of fault, and very importantly, you have a massive deep aquifer in a fractured domain, which is, as we will see also, basically a trapped aquifer from a very long time, heavy brine that is there for a few million years, and that the system is basically exploiting, and it's a vision of much more a mining vision, like how to access to this fluid, taking advantage of the fact that you have the fluid there, but also that you have a set of faults that are possibly good conduits, and trying to minimize or to separate the 2 features of a fault. One is that it is an hydraulic conduit, but the other one that it is a fault, so it's the host of earthquake. Yeah? So induced seismicity is not far from the problem. So how to balance and manage the fact that you want to take advantage of the hydraulic part, but not on the seismic part. Yeah? So this is one of the questions. So for this, the strategy is mining, and the ore is basically, there are several actually. There is the heat, but the heat is already transport or mobile because of the fluid. And as I said a few minutes ago, the fluid is also rich in other materials like lithium. And so extracting the fluid not only provide heat, but also provide resources like lithium and possibly others. One of the others is native hydrogen. But in this vision of mining, there is the ore, different ores, but there is typically, as we are for mining, there are waste. And now we come to the vision that actually the fluid that has been extracted and from which you have extracted the heat is a kind of waste, and you have to get rid of that fluid, and then there is an issue about re-injecting that fluid at maximum rate. Typically in those projects, the rate of re-injection is the limiting problem. It's typically easier to extract than re-injecting, And most of the problems typically related to induced seismicity are coming from this re-injection part. Then there are a few subdivisions, like focusing on the faults or trying to find some sub-reservoirs and combining reservoir visions in terms of fluid distribution outside the faults or not in the faults and so on. There are questions about balancing out the recharge of the system when you extract how the system is recharging the zone where you have depleted the fluid, and how to measure this recharge is a quite challenging problem. In the Strasbourg case, this was a very important issue. Okay, so I think from this I more or less set the scene. This figure is just to remind that this EGS in this vision is two issues, and the ore, which is the heat of this fluid, relying on this fluid, and the technique for mining that, for extracting this. And this, I insist a little bit on this because this is very much related to the risk issue, actually. The risk in terms of for those projects is there is two types of risk, and basically there is the geological risk, which is in terms of mining is to find the ore. So where is the fluid? How much fluid do I have access? Is this fluid mobile? And how sustainable in terms of fluid access is the project? Can I have? Do I have a lot of natural fault to access to this fluid, and which will limit my drilling? Basically, if I can take advantage of natural faults, I will limit the drilling. So I will optimize that. And according to that, you will have different mining effort, and typically the second part of the risk is that the mining, in this case, which is basically mostly hydraulic stimulation, is where the induced seismicity is, and this balance between the effort you put in the mining, in the techniques for pushing or enhancing the fluid migration, is typically controlling the induced seismicity, which is very closely related to the public acceptance of this type of project. So my message is to say here the strategy of the projects, either engineered or enhanced, with a good knowledge or little knowledge of the resource, with different efforts in modifying the natural material, will impact very strongly the seismic risk and definitely the public acceptance of the project. So this is why, for the moment, I think typically in France we are more in the enhanced type of EGS. An extreme case of this one is a recent project closed by Soufouret in Rittershofen, where they didn't have to stimulate, to modify the natural material to have a good production of the heat, and being very close to this case of conventional geothermal. Okay, so this is to summarize the vision I would like to introduce on this EGS concept. And now I would like to say a few words about the mechanism that might relate the project to the induced seismicity. So it was a lot of it already discussed this morning, and possibly more later. The two main impacts is, of course, either modifying the pressure, the fluid pressure in the system, typically the fluid pressure along the faults, and this will have an impact on the induced seismicity. And the second family of effect is to modify the solid stress around the fault, and this will also have impact on the fault and will have impact on the seismicity. And to be just a little bit more quantitative, but you had more detail this morning, is in terms of more Coulomb, the pressure effect will have basically three major impacts. I insist on one that was not so much discussed this morning, is that in those reservoirs, there are typically a lot of pre-existing fractures. And first, when you change the pressure, you will impact the friction process before the fracture process. Yeah. So you might have an hydro shear because you're shearing and you have slip on a pre-existing fracture. This is what is going to happen at first. And second, if you push the system further in terms of pressure, you might enter first the hydro shear domain, so this slope, or if you go even further, reach the limit of hydrofrac when you don't have shear, you just have an effect in pressure and create hydrofrac in the principle of opening, pure opening of the system. So yeah, this you have already a very important knowledge of this. I just insist on the fact that there is a significant difference between friction and fracture processes because in those systems, because of the pre-existing set of fractures. And about this induced seismicity, this is a map of the major case of induced seismicity. And in red, you have the major ones related to geothermal energy. And they are not the one responsible for the largest induced seismicity, as it could be for other like hydro case or some mining case, but hydrogeothermal energy is responsible for some important one. The most recent and most important one is the South Korea, the Pohang case, where a magnitude 5.4 was triggered. I will come back to a little bit to this, and I put the Strasbourg case. I will also introduce, which led to the end of the Strasbourg project recently with a magnitude 3.5 earthquake. About those earthquakes, for those of you who are not so familiar with seismicity, here is an interesting table from Zhang et al., who are summarizing the typical feature of earthquake and the scaling laws of earthquake. The magnitude is here. Intensity is here. So intensity are the quantification of the damage at the surface, and magnitude is related to energy, as you know. I put a lot of stars, some new ones also related to the Strasbourg case here. There is also the Basel case, Nando, Sulfuré. So geothermal energy is producing earthquake typically here, well, except for the Pohang one, which are a bit of above. But I want just to say that they are still much smaller than the major natural earthquake, significantly smaller. Even if they start to create some damage, the limit of damage is basically here. In terms of intensity, you see you go from weakly, largely felt to start to get some damage. And the boundary is typically at magnitude 3.5, I would say. And that's what happened in Strasbourg, and where it happened to be some damage in the buildings. So the big geothermal earthquake, just to get an idea, Strasbourg case is one of a good example, are earthquakes that involve area of a few hundred meters of rupture, a few hundred meters, just to have numbers in mind. The slip on this is about a few centimeters, and the depth is mostly controlled by the depth of the project, so this is 4 to 5 kilometers, so quite shallow compared to a natural earthquake. So that's the message. And another concept I want to finish with about my general introduction is the difference between induced and triggered seismicity. in the sense that there are a few definitions from different sources, but the concept is that there is two classes of induced seismicity. The one that is controlled by the modification introduced by the anthropogenic work, I would say. So induced, strictly speaking, is related to the perturbation, the mechanical perturbation introduced by the human activity. And it's important in terms of concept because knowing the perturbation that is introduced is an upper limit of the earthquake that is going to be produced. And there is a strong control of it. But basically the dangerous one are the triggered one, which acts as the more droplet vision is that the perturbation that is introduced by the human activity is just a triggering process. Most of the loading is due to the natural tectonic loading. And of course, this is difficult to predict because a small perturbation, mechanical perturbation, can trigger a large earthquake, and the Pohang earthquake is one of those. So to finish with make transition with my two case studies is about an overview of deep geothermal energy EGS in France. So most of it is standing in east part of France, so close to Strasbourg. Strasbourg is here. Soultz-sous-Forêt, I mentioned, is 50 kilometers north. An important project related to Soultz is Rittershofen, 6 kilometers of it. And because it is close, all the exploration and the knowledge of the underground from Soultz was applicable to Rittershofen case. So they could develop that project with little investment on the exploration, basically. And it's a sort of a migration process from a well-known site. And it's a success. It's a very big success. So the lesson is you have to have a good knowledge of your underground to make it successful. In the Strasbourg case, it was a couple of projects. There are a couple of projects. Two of them were stopped from legal reason and political reason. But the Van den Heim one I want to discuss a little bit is 10 kilometers to the north. And could be considered as close to Soultz, but we will see that it was sufficiently different to make it actually a very different project. And the knowledge of the underground was definitely not sufficient. But in that region, so I discussed a little bit the success of these two, but this success is also relying on a long history of the exploitation of the underground, mostly because of the Pechelbronn oil field. So there are very large number of wells in this area, a few thousand of wells that provided extremely important knowledge of the underground. And it's confirmed in a way what I was saying, a good knowledge of the underground is necessary. And yes, and just to finish with this recent development, especially to the north, the blue stars are the projects that are planned, and you see that there are a lot around the Soultz area, and this is mostly because of the lithium, the cogeneration of the lithium with the heat that is coming, and big pressure or the big challenge and expectation from this lithium production. So from this, I will go to my second part of the talk, the case study of Soultz-sous-Forêt. I will make it very intuitive to start with. So sort of a vision from Soultz-sous-Forêt with the two locations of the wells. You look to the north, you see the Rhine Graben in this area and the Vosges Mountain to the west. We are basically 50 kilometers north to Strasbourg. And what is very interesting in this site, it's a sort of coincidence at this stage, is that it exists a very nice database for those who are interested. There is actually a public 3D geological model of the area, which is quite unique in France. And from this you can build a cross-section by yourself below the city of Sul-Sous-Forêt, and this is an example of that. And where the project is going on. Major feature to remember or to have in mind is that this project is going to extract heat below the sedimentary cover. So there is a basin of 1.5 kilometer, and the geothermal project is going below that in the granite, in the granitic basement. This is the general geological setting. So if you want to visit this, you will see this type of infrastructure. From the surface, you see, of course, very little from what exists. You would see the power plants with the 3 major wells and the heat exchanger of this. So it could be commented, but I don't want to say much. But just to say also that this site used to be a scientific pilot, but recently in 2016 it became a full industrial site. So the link with the site is between the scientific community and the site has changed very significantly. But still, the site is very active for science, and just as an illustration, I don't know if it's a good one, but it gives some hint. I searched on the Web of Science the citation of Sul-Sous-Forêt, and all papers, and you see a rise of the number of citations recently, even if the project started in the 80s. Even now there is still a lot of use of that site for developing research activity. If you have interest, there are now some data repository to get access to those data. I promote somehow this because I'm trying to push that. You can access from the Strasbourg database, which is a CDGP. Here is the address, and this site is a local node of a European program, the EOST program for distribution of earth science. And so you can also have access to source data through this site. And here is a sketch of the site. The picture I introduced before, this is what you would see from the top, but actually you wouldn't see much. Most of it is below, I've mentioned. And here is a sketch of the main features. The sediment layer on the top, 1.5 kilometer, and the wells there are 4 major wells, GPK1, GPK2, 3, and 4. GPK1 is not used anymore, even if it's a historical one. It's not used anymore for well issues. It's getting some problems with the well. So only the 3 other wells are used. They go down to 5 kilometers, which make them very deep boreholes and very unique. They are at depths separated by 600 meters. The open hole sections are only at depths, so it's not an exchanger over all the wells, but just at the very bottom for about 500 meters. And so there is 1 production well, GPK2, and 2 reinjection wells. And this is related to the point I mentioned, is that reinjecting the waste aspect is difficult, and they use 2 wells to reduce the pressure in the reservoir and to reduce seismicity. So this is the reason for it mostly. And the production well is GPK2. So the system is closed at the surface, heavily closed, and this is mostly for environmental issues, because the fluid that is extracted is a heavy brine, It's 3 times more loaded in salt than seawater. And this is the geothermal fluid, and re-injected closely at the surface. And the system is looping, it's quasi-looping, actually it's not looping basically, because at depth only a few percent of the fluid that is re-injected is pumped. It's basically 25% of the fluid that is injected that is produced. So the system is very far from being closed at depth. So in that sense, it's not exactly a geothermal loop, but it shows that it's really a mining issue. You're extracting more new natural fluid than you're re-injecting. And the second feature is that the geothermal loop is basically the one I just described, with the features that are here, production at 150 or 60 degrees, and re-injection those temperature and so on. So this you can read here. But energy is produced by a secondary loop that I will not comment, which is an ORC loop to produce the electricity. And typically, if you compare the thermal power of this system, it's 11 megawatt thermal produced by the geothermal loop. Basically, 1/10 is transformed in electricity, so about 9/10, actually 85% is lost, and is basically sent to the atmosphere through this heat exchanger. So the efficiency of such a system is not so high. You recover the 10 factor I mentioned for the at large scale. It's somehow related that electricity is for such a system is not so efficient, and why the cogeneration of heat is so important because of this poor efficiency of the system. So more could be said, but I want to be not too long. I insist on one aspect, which is the fault network. And the fault network actually was discovered during the project. It was not discovered before. And typically, one of the main faults that is at least known, but still not very well understood in the role of the system is this fault, FZ 4770. It's a few kilometer fault. Here it is drawn with a 3 kilometer diameter. It's not fully known. It is shown here also, and it's far below the sedimentary, and it was not really known or imaged from a geophysical technique. And this fault is basically cutting the 3 wells, not GPK4, but at least the three others, and it has a very important role in the behavior of the system. And a few comments also on the origin of the heat. In this, as I said, it's an enhanced system, so you need to know very well the natural condition to optimize this, and you learn a lot from that. The source case is providing a simple measure, a quite simple measure, which is just the temperature profile in that area. But this information was not known before the project, and is still a very rare measurement, especially a temperature profile at equilibrium in a deep well like this is a measure that is extremely costly because you need to make the wells at 5 kilometers, and you need to wait for an open well for a few months for getting the thermal equilibrium, and this is very seldom, so we have the opportunity to have it at source. And this is what we see, the upper limit here, with the very strong gradient at the surface. 1 kilometer basically 100 degree. So this is 100 degree per kilometer, which make it one of the highest geothermal gradient in Europe, at least in that area of Europe. There are some other cases with larger gradient, but it's a very important one. And define basically the thermal anomaly, because at depths you recover a thermal gradient which is more classical for a context like the Rhine graben with a basin of that type. And the anomaly is defined here as the excess of temperature compared to this general trend. And this is what is the resource. And the origin of that is still quite debated. It's very much related to some hydrothermal activity and large-scale convective cell, as we recently re-explored from a numerical modeling, THM modeling coupled to reproduce such an anomaly. So you have the computation in green and the data, the measured profile in blue here. And from such a system, you can reproduce the circulation that is responsible from this thermal anomaly. You see the velocity of that convection is very low, a few centimeters per year. To my knowledge, today there is still no direct measurements of that velocity. It's so low that there is no tools to measure it directly. It's confirmed. I mean, it's another way of saying that imaging this fluid aspect, which is the resource, is extremely indirect, and a lot should be done to do some direct measurements. And the variable, the lateral variability involved a scale of a few kilometers. It's about same as the height, so 4 kilometers for those cells. And of course, knowing this will impact very much the exploitation, because making a project in an upwelling is quite different from a downwelling. And this is a sort of implication of that. Another one that you might see from this figure, and it was a big surprise from our simulation, is that the flow is going through the transition from the sediment to the basement in a very transparent way. So there is a very little control of the geology on the circulation, and this is quite puzzling, because it has strong implication. Nowadays, typically exploration is on the solid parts, so on the rock, and with some strong assumptions of link between the rock and the fluid content. And if this result is true, it means that you're losing the connection between the rock lithology and the nature of the fluid that is inside, which makes the exploration much more challenging. So we confirm that through some numerical modeling, as I said, but maybe time is running. So I will skip the demonstration of that, but if you have questions, I can go back to it. For the physics and just some suggestion about possible development, this is an illustration of something we can do with the code, is to change the viscosity of the fluid. Sometimes in those projects there is a lot of work on the rock properties, but there is very little work on the physics properties of the fluid. And you see that if you change slightly the behavior of the viscosity of the fluid, namely considering the one we used, which is temperature dependent, and that is consistent with the other heat flux and many other properties. If you use the viscosity at depth or the viscosity at the surface, you change dramatically the resource. There is no more hydrothermal system if you reduce slightly the viscosity, increase slightly the viscosity by considering it at low temperature. Or if you change the viscosity, you have basically a cold convection with no, basically no interesting gradient, so no resource. So the impact of such a physical property of the fluid is dramatically important. So the circulation of this has been modeled, and the role of gravity and many aspects. Origin of the fluid has been explored, typically from geochemistry measurements, and it has been shown that there is a family of fluid with a high concentration of lithium that has a specific origin in terms of geology. There is a lithium enrichment which is made mostly due to the geological history, in particular the period of the alpine period of the basin, where it was a lot of trapped lake in the areas, and solar conditions which are responsible for a strong enrichment of the water in lithium. And this has been trapped after, and this is the fluid that is used now for geothermal exploitation, and this is why it is also planned to exploit this lithium content. Okay, so to continue on this the source lessons and this link between geothermal enhanced system and induced seismicity, I will comment a little bit on the induced seismicity observation in source. A very nice picture from Nicolas Queno a few years back on the induced seismicity during the major stimulation of the wells. You can recognize the 3 and 4, GPK1, 3, 2, 4 wells, and the cloud of seismicity that has been measured during stimulation. So each of these clouds contain a few thousand of earthquakes, and of course the knowledge of those earthquakes have been very important in the understanding and the lessons from the induced seismicity in this project. And just to illustrate that, I want to give you a few information about that. The first message is that in SULS it was tested 2 types of observations. I mean, stimulation I mentioned, but also of monitoring tools. Some surface seismic networks, like it is drawn in this figure. And one important of SULS project is that it was existing oil wells, and few of these oil wells were instrumented in with a seismic borehole instrument at depths and typically below the sediment cover. So the wells were so deep that they could go below the sediments and enter the granite, and the instruments were basically at the top of this granite monitoring the clouds, the seismic cloud, a few very close by. And you have a comparison of what is observed when you have such a unique set of boreholes instruments on the left, and a few thousands of events that are measured, and the same stimulation seen from only a few sensors at the surface. So it was only about 100 events seen from the surface, and 15,000 seen from these borehole instruments. So instrumentation is a key point for understanding what is happening, and quality of data is very important for that. And the development that were done at that stage to install this type of instrument in extremely aggressive environment. It was more than 100 degrees, 120, 130 degrees, extremely saline water. So it was a big challenge, but this is one of the reasons of the success of this pilot set. And from this, it was done some stimulation. One of them is sketched here. When you do see the flow rate in black, and the increase of the flow rate, and the pressure response during that test, and you do see that despite the continuous rise of the flow rate, the pressure necessary to have this flow rate is basically saturating showing that you have changed the permeability of the reservoir significantly during this test time. So that's a type of stimulation. Massive stimulation were done at that time, a few thousand cubic meters. So nowadays this is basically forbidden. So we have that kind of advantage, scientifically speaking, to have access to this type of large-scale dataset. And this is the type of dataset that are on the website and the database I mentioned earlier. Another feature that makes the site extremely interesting scientifically is that it was done some time-lapse borehole imaging. A very simple concept, but very useful. It's measurements of the geometry of the wall of the borehole, but it was done before stimulation and after stimulation. And by just this time lapse, you could measure the difference between the two and evidence the slip of the wells or the shear of the wells related to the stimulation, because you had the status before. And a very interesting measurement was done at the time. One of the first is that the well was sheared because of the stimulation by an amount, a few centimeters, that is completely incompatible with seismic data. So the shear that is observed would have been consistent with a magnitude 4 event, but the biggest one that was observed was magnitude 1.9, so much smaller. So it's the first time that a non-seismic slip, important non-seismic slip, was observed in such a project and related to hydraulic stimulation. Okay, so that I skip. So maybe since time is running, I will skip a little bit of the seismic information I wanted to share about this high seismic slip, the techniques that are the seismic signature of the high seismic slip. Make it start to be a little bit complicated, but this is what is used because of this lack of direct access to the system. We use very indirect measurements, and we use the signature for very small earthquakes, like small acoustic emissions, that are the signature of high seismic slip. So this could be in the domain of the ductile processes. I skip this. If you have more questions about the seismic features, I could comment that, but I will skip that. And I will come to this, some recent work we did with this seismicity, exploring those datasets, because it leads to some new vision of what is happening during hydraulic stimulation. We have some interpretation, but not fully, possibly not fully understood. The observation is the following: is that during such hydraulic stimulation, if you look at the statistics of earthquakes that are produced during this event, you basically can separate two populations of earthquake. You see a Gutenberg-Richter distribution of earthquake. You see a first family, which has typical B value, and another family with a similar B value that is coming later. And this is two independent families. And actually, these two families can be shown to correspond to two populations of small earthquake of different size. So the first population is from small earthquake with a radius of a few meters, and the second population, which is a much broader distribution of earthquake. And actually, what we observe is that these two populations are coming into the system according to the injection pressure. At the beginning, from low injection rate, this system is typically producing a small earthquake in size, and later on there is a new family with much larger earthquake. And if we phrase that in terms of some geomechanics the reservoir and link the seismic signature and the geomechanical loading, we can lead to the following vision of the stimulation. So you have a map of the seismicity here at two different depths and at two different times. So this is the upper one at the beginning, and this is the down one at the beginning. So it's a cloud around the well. And when the stimulation rise develop, it develops two type of fractures that we are sketching from the directions in colors here. So at depths, it first develops some trend that we see at the end of the cloud, which is basically the orientation of the pre-existing fracture. So the first part of the system where we do have this small earthquake is onset of rupture on pre-existing fault, and this is where also the high seismic system is expanding. So pre-existing faults are in play. They produce basically high seismic slip, and at some point, when the pressure, the flow rate is rising, you go to another regime where you start to develop some shear, the blue ones here, the shear crack, some new interface. The first one was on pre-existing one. New ones in shear mode. These are the blue ones. And when the pressure is rising so much, you will reach hydrofrac and another orientation. So by combining the knowledge of the mechanics, the regional stress field, and the geometry of the seismic cloud, we can rebuild a sort of geomechanical history of this stimulation. And again, this is another vision of the same stimulation, where you look in time and depth the evolution of the seismicity, plus in color and in size, the size of the earthquake. And you definitely do see a trend during the hydraulic stimulation. First, the very small ones around the open wells, and it's coming down over the open well part. And after an increase in flow rate and in pressure, the development of the larger earthquake, and basically the development of a large-scale shear fracture in the system. And what is plotted here is a set of curves that sum up this stimulation, the evolution of the depth of the seismicity, also the evolution of the radii of the earthquake, with these two steps, the small one and the large one after. And it compares this vision to, I would say, a more classical vision, which is, for instance, evolution of the B value during a stimulation. And there are a number of groups that are trying to interpret this evolution of B values during the stimulation. Our claim is that it's very difficult to interpret that. There is more knowledge on the asperity size, which is two steps and a more direct interpretation. But this compared to other classical value like the seismogenic index that has been inverted and so on. So comparative vision between different schools, I would say, is possible from this graph, and could be commented more if you have questions about it. From SULES, we learned a lot about fluid-induced seismicity. One of the first work on this by Nicolas Shapiro was to interpret the boundary of the seismic cloud through time, the distance time, so the diffusion vision of the seismicity. And from this assessment of the hydraulic diffusivity of the reservoir. And this was very famous, I think, used in many cases to assess the development of seismicity and predict also the development of seismicity. But as this figure shows, there are still some open questions, because quite some seismicity is happening outside of this diffusive part, and it's not following the same process. So now there is still a lot of work on trying to have the other vision on the origin of the migration of seismicity and not just fluid diffusion. One example is what happened in another stimulation in SULEM, and this is a very interesting observation that François Cornet did a few years back, that is still very open. Is this vision that during the stimulation of GPK2, when the fluid is injected, this is clouds, a map of clouds. Each red bar corresponds to one snapshot here, so from 1 to 14 to 13 is going this way. 13 is the last one. And you do see the development of the crack during the stimulation, migrating, extending in that direction progressively. But one of the interesting observations is basically the two last one, is that the seismicity is very confined along this shear crack, this hydro-shear process, and it's only during shutting, when the pressure is decreasing, that it migrates outside of the crack. So it's a completely opposite vision from a diffusion process, because it's when the pressure is reducing that the system diffuses at maximum. So this observation is still debated and an open vision. Another observation that is still open is something that was also related to the work of François Cornet, is this type of images, which is tomographic images of the velocity, the wave velocity during the stimulation. And you have 3 graphs here that correspond to the 3 colors here. So at 3 different steps of the stimulation, and typically the one in the middle is correspond to the yellow one. This is when you have a strong rise of the flow rate. And when you have a strong rise of the flow rate, anomaly in velocity that was existing before is disappearing and reappearing after continuing to increase the pressure. So why is the system changing so fast? This is a kilometric scale with a time step of a few hours. In velocity is something that is very open, still very open. Yes, so I will skip this, I think. It was about stimulation efficiency. I will say just a few words to finish with. Time is still okay? I think so. Yes. Okay, I will say spend the rest of the talk on the third part of what I wanted to introduce, which is the study of the Strasbourg case, the London case. And I will introduce that with this figure that you basically already partly know, because this figure is a geological cross-section from SULEM to Strasbourg, from the geological model that I introduced before. So you recognize the sketch of the SULEM wells going down to more than 4 kilometers deep, the depths quite far below the sedimentary cover, deep into the basin, into the granitic basement. So this cross-section is passing through the Rittershofen site that I had no time to present, but it just showed that this project was much shallower, half the depth, focusing on the transition between the basement and the sediment. And it's a very successful project. So shallower and focusing at a shallower depth where, if you remember, is the maximum of the anomaly in terms of thermal anomaly. So it's optimized in that way, targeting biggest anomaly, the biggest part of the anomaly, and at the shallowest depth, and make it successful. So a few messages behind this. And the Strasbourg case, which is as deep as the SULEM case, targeting also this transition between the basement and the sedimentary cover. So the concept is the same, assuming that most of the interesting part is at that domain, but because in Strasbourg it is at the center of the basin, it is much deeper. So meaning much deeper, meaning impact, yes, meaning more complex in terms of drilling, and also less amount of data, so poorly explored, and that was a failure. So this is a first message. So this is a sketch of what the Van der Line project is. Drilling into the sedimentary cover that is about 4,000 meters. Actually, this geological model is not correct here. There is a few hundred meter difference between the model and the depths that Fonroche experienced. So just to say what was the precision in terms of geological model and impact on drilling. And the target was to go below and then deviated and then cross one of the faults that is drawn here. So really targeting a major fault, contrary to the SULEM case, but as it is done in the Rittersofen case. And this is the project. All the surface installations were already finished, but the geothermal loop was not validated before finishing the surface installation, so that was a kind of risk. And this is something that they have to face. But this project led to 4 major earthquakes, and this is the 4 maps that you see here. So it's an intensity map. So it's a map of the damages or the feeling of the earthquake around the city of Strasbourg. So the city is here in all this graph, and the boundary between France and Germany is here. So those earthquakes were of magnitude 3 to 3.9, and you could see that they were felt a few hundred kilometers away, and that the basin, the Rhine-Graben basin, has a strong amplification of the effect. And most of the effect is larger along the basin, so there is a basin cited. And intensity was at maximum 5, so started to be some damage. It's actually 4,000 cases of with insurance. Some discussion with the insurances to get some support for fixing those damages. So it's quite a strong impact both on the French and the German side. And these 4 major earthquakes that are in red here were also having in between other felt earthquakes, but slightly lower with no damage of magnitude larger than 2. Magnitude 2 is the threshold for being felt. And this is the sequence from 2019 to 2021. So I just want to give you some short detail about this, because this is really important illustration of induced seismicity related to deep geothermal energy. So this is a detail of the map, the city of Strasbourg with a Google map. The location of the project with the site of the wellheads here with the yellow marker, and the wells that are here, the trace of the wells. So you see some important horizontal component of the wells. And the seismicity during this crisis was basically in two clusters, one attached to the wells and one not attached to the wells, with a gap of a few kilometers with no seismicity. It was a big debate because the first important one was here, so quite a distance from the well, and how much it was related to the geothermal activity was an issue. Yeah, it was a traffic light system to describe this, but actually the red level was at about 2, but the system overpassed this alert level many times, and even very much because as I said, the limit was 2 and the largest one was magnitude 3.6 in local magnitude. So this is the network that was around the city for monitoring that, with some new types of sensor, but I will not detail that. A first comment is to say that seismicity, this is interesting that my mouse is moving. Anyway, the seismicity before the project was basically not existent in a radius around the project. In 5 kilometers in radius was no seismicity before, and you have to raise the circle of that is around the project to start to see the seismicity, and actually you start to see the seismicity in subsurface area. So naturally it was no seismicity in the area, and this was one of the arguments to say that it was related to the project. So these are some detail about the history of the operations on the site during this period, starting from the drilling and continuing with the stimulation. The first major event in 2019. The continuation of the drilling, despite the alert from this major event, and the restart of the project basically a few months after, with circulations, and when circulation started, the significant earthquake that were occurring. And interestingly is that the first very important observation is the one I mentioned before, is that most of significant seismicity was happening very remotely from the wells, at a few kilometers from the wells. A second interesting observation is that the largest one is actually the latest one here. And it's typically 6 months after shut-in here. So why is the largest one 6 months after shut-in is still a very open question. This is something we can see if we combine the history of the operations and the history of the seismicity in the two domains, in the northern cluster or in the southern cluster. You have the history from 2018 to 2020, and you could see the signature in seismicity of the different parts of the operations. For instance, drilling had a little bit of seismicity here. Mostly the stimulation at the end of the drilling has some signature, and stimulation at the end of these 2 phases of the drilling was the second part of the seismicity, and some jump of the seismicity at that period, and the restart of the operation leading to the major events attached to the GT2. GT2 is the reinjection well. So this is where also I linked to my first comment. Reinjection is the problem, where it could be the problems, and this is exactly what happened here. It's not reinjection that was issues. And to give you a hint about the origin of this remote seismicity, here is a geological map of the area. So you have the wellhead here, and the well traces here, the northern seismicity, the southern seismicity, and from this geological map, which is a cross section at 4,000 meter depth, you do see the trace of this fault that they were targeting. So this fault is actually linking the two clusters very nicely, very directly. And so there is a geological object that links the two clusters. So we expect that it is because of the behavior of that fault that there is this connection. Another observation that you can see is that this cluster is exactly lying at a place where the fault is as a kink. The direction of the fault is slightly changing, and this is exactly where the cluster is developing. Yeah. So the mechanisms that are really responsible for this remote triggering are not fully clear. It could be many, but to find which one was the dominating one is still open, and we are working on this in terms of research activity. And the problem is that, and it's a very fundamental problem for those type of projects, it is what is the size of such a project. And it's very important because what should be monitored, which domain should be monitored to monitor such a project. Here the monitoring network was focusing on the close surrounding of the project, and actually most of the significant part of the seismicity appear at some distance, basically behind the seismic network. So we have a poor knowledge of that activity, and it questions very much what is the size of such a project, and how should be designed the size of the domain which is considered under influence of such a project. I think I should finish soon, so maybe to finish, I will just say finish by this figure. It is about the main explanation we have for understanding this seismicity. So it's a very simple analysis, as you will see. It is coming from the knowledge of the stress field in this area. So you have the Rhine-Graben here, the city of Strasbourg, Karlsruhe is here, and Basel is here. And you have the map of the measurements of the stress in that area. And first observation is that there are not many measurements in the area of Strasbourg. So poor knowledge. All the knowledge that is existing is basically the one from SULEM, where it was some measurements of the stress field. So in this analysis, the stress field from SULEM was used. And if you use the stress field of SULEM and look at the main fault orientation that exists in that area, there are three families of faults. Basically, it exists one of them that is getting very close to the failure criterion that we know, and this is exactly this direction along which were the major earthquake when the stimulation were developed. So the simple explanation that we have in mind now is to say that they were critically stressed, and as soon as stimulation started, they triggered this family of earthquake. Okay, I think I should stop here. I could say more about Strasbourg if you have questions, but this could be part of the discussion. Anyway, thank you very much for your attention, and if you have questions,
Thank you very much, Jean. Thank you very much. Well, please go ahead with questions.
Yes, thank you, Jean. For the project in Strasbourg, is it temporarily stopped or definitely stopped, or what is the future of the project?
So the situation is a little bit complex, as you can imagine. So formally, it's a long story, so I will try to make it short. It was a decision from the prefecture to stop it definitely, but Fonroche went on court and got this decision cancelled. So I think formally it can be continued, but the prefecture said that to restart, because they overpassed the critical threshold, so they need an authorization to restart. And the prefecture said they will never give back this authorization. So this is the status for the moment. Yeah. But recently, this project, I mean, Fonroche has sold the project to the group Ardern company. So it has been transferred to this new company, and they didn't provide a clear vision of what they want to do with the project for the moment. Yeah. So we will see. But it's a big debate, a political debate in the area, to know what to do with this. Of course, it was a lot of controversy and controversial debate during the crisis. And so the city is in between a strong opposition and a moderate opposition, in the sense that just after the event, I think it was a very strong opposition, but because of the Ukrainian crisis, the situation is also changing, because Strasbourg has strong involvement in the use of geothermal energy in their program for climate evolution or energy transition program. So it's an in-between situation. So I think it will evolve in some future, but I'm not the one who is deciding that.
But I mean, apart from the political situation, in terms of controlling or mitigating the seismic risk.
So the situation now is the wells are, it was shutting in both wells, so they are closed. There is some monitoring there is monitoring of the seismicity from our institution, the BSF radar. And Fonroche is maintaining some of the sensors, or most of them. And so there is some sort of minimum monitoring, but there is no plan for restarting some activity or doing something with the wells, basically. Even if there is some pressure from the authorities, the reason is that such a well cannot stand without activity by law for a long time. So it has to be some plan, and I think there will be some shortly some plan about what to do. And the main trend we are hearing is that could become sort of research site, but there is no clear plan about that.
And from the analysis of the event, now a posteriori, could this activity or the earthquakes that were induced, could they be avoided by, there was some, you think, some problem in the control of the pressure, or some
what I can say is that I could comment on this figure. With more time I would have shown this figure. It's what we think, because it was an expertise on this project, and one of the major, it was few major conclusions out of that project. One major conclusion is something I was implicitly saying a few times, is that the exploration phase was not sufficient. So the a priori knowledge of the area, of the stress measurement of the stress state, the geometry of the faults, the lithology, the depths, many aspects were not sufficiently known. So that's one conclusion. Another one is this figure, is the monitoring of the injected volume. Because we rebuilt the history of the injected volume during the project. It was not monitored during the project. And you could see quite important features. So this is the volume during the whole period of the project, and you have the first phase that leads to this earthquake, and then the second phase that leads to these two major earthquakes. And during this first phase, you could look at the black curve. The black curve is the overall net volume. So the balance between the injected and produced volume, so the net volume. And you could see that there is a quasi-continuous rise of that volume until the event. And basically, this volume is about 100,000 cubic meter. And this type of volume is very compatible with some classical estimate of the maximum magnitude with respect to the injected volume, like Magar argument. And in such a law, you could have predicted that you are entering a sort of risky domain with respect to the definition that the company imposed, is that the alert level is a magnitude 2. If I can show it on this graph, you have the magnitude as function of injected volume, and the square, the pink square are the case from Van den Helm. And you could definitely see that those volumes, they are compatible with much larger events, event close to the type of seismicity that happened, that are definitely larger than the magnitude 2 threshold that they were trying to fulfill. So to answer your question, this is what we was considered as something that was definitely missed, is that following this volume would have been a kind of alert to avoid producing such large earthquake. And then you could question why they injected so much. And this is it was quite a surprise, because 100,000 cubic meter is not such a small volume. And it's very specific from this case. They had access to the water that is used for controlling the pollution of the site. So this site used to be a oil refinery, and it's extremely polluted area. And to save that, they are pumping heavily the water below the site to have the water table going down. And this water is kind of accessible. And this is a huge volume. And they use part of the volume to inject it. And this is it's not so clear why they did it. I mean, it's clear in the sense of stimulating the reservoir, but it's extremely specific of that site. In any other site, you wouldn't have access to such a mass of fluid, and obviously it would have changed the story.
There was another question. Thank you, Professor. I have a question about the SULEM case. They used to present a lot of induced seismicity data during the geothermal reservoir stimulation phase. But in current state, the power plant has been stable and operated, so which means the circulation has been stable set up in the geothermal reservoir. So is there any new seismicity can be monitored in the stable state? So,
okay.
So what is the reason of the?
It's a part that I had to take out because of the time limitation. But one of interest of SULEM is that there are a couple of measurements during long-term circulation, which is your question. Often when we deal with EGS site like this, we have in mind stimulation, so temporary massive injection. But in SULEM there is some tests during long-term circulation, and so there were a few, and so many aspects could be studied from that. But one of them is really this impact of the re-injection pressure on the control of the seismicity. And there is a very non-linear aspect to it, like very empirically. We don't have a clear understanding of that, but empirically they found a sort of a rate injection for the re-injection that limits significantly the seismicity. So that's what they did empirically. They first split it on two wells to reduce the the pressure, and by some empirical tuning, they found rates and pressure to inject to downscale or reduce the seismicity very significantly. So strategies for monitoring, for reducing the seismicity, if it's your question, from the injection was obtained during those long-term circulation testing.
Maybe I have a follow-up question on that, on SULT. So the performance of the well pre and after the stimulation is not so different, right? In terms of liter per second of some difference in pressure.
I have to check if I have the figure. About that in my slides. I skipped them, I think. So what you're asking is about the injectivity increase from the stimulation.
Yeah.
So the different wells. Yes, I have a figure that shows a little bit this. This is one of the figures I skipped, so I can answer that. Yes. So this is a injectivity index. For the different wells, according to the different stimulations, which I think is part of your question.
Yeah.
And you could see that the behavior of the well is quite different. So GPK2 has a low initial injectivity, which is the yellow level here. And hydraulic injectivity, hydraulic stimulation rise or increase the injectivity quite significantly. It's almost a factor 10.
Yeah.
So still not a very huge value, but still an impact. And then the chemical stimulation did a little bit of the work, the rest of the work. But altogether, you see the limit is 0.5 liter per second for this specific unit, but it's not so much. In Rittersofen, in that unit, it will be 2 to 3. So it's much larger. But you see the difficulty, and that's what I still put in an open question, is in other wells, the work is quite different. And typically the one in GPK3, which has a larger initial injectivity, the hydraulic stimulation had a smaller impact, and a little impact actually. Mostly because it was existing already significant fractures with a high permeability that make the development difficult. So there is some lessons from this because of all the stimulation in different cases. For instance, close to an important fault or far from an important fault with a high initial injectivity or not, and you have some lessons from this.
And they inject from GPK3?
But all the wells, you mean now? Yeah, now they reinject from GPK3 and a little bit from GPK4. Okay. Yeah. Yes. Okay.
Thank you very much.
Thanks everyone for staying here, and thanks Jean for introducing all the concepts behind the geothermal energy development. So I'll build upon that from slightly different perspective, maybe more from the mechanics and of fluid-driven fractures. Its application to geothermal is only one aspect of it, but that's what we're going to focus today. So my lab is mostly working, so I would say only working on this mechanics of fluid-driven discontinuities, so fractures and faults, so hydraulic fracturing, but also fluid-driven reactivation of fractures. So I think Jean had a much recent slide on that because I could not find the recent numbers, but Jean gave them. That's 2017. And regarding electricity production, so now the 1/10 of the thermal energy that can be transferred into electricity production, and so it's still a very, very small number of the total percentage of the worldwide electricity production. As you can see, most of it is US, Philippines, Indonesia, Mexico, New Zealand, Italy, Iceland. Basically, it's places where it's hot. There are some shallow thermal anomaly for this. Also, the two types of reservoirs, so hydrothermal, petrothermal, okay, and the different type of variation around the petrothermal that John alluded to. Most of the ones that are producing lots of electricity are basically hydrothermal system. Okay, low heat anomaly, quite shallow, can be produced with a huge energy output. So with Tuscany, Lardrello, the geyser in the US, and other parts of the world. And the EGS, so it's different variation of it, which have much less success and actually probably none. I think the SULEM case and a few others are the ones that are really working. So there is indeed a correlation between where it's hot, where you have geothermal plants, and when you have earthquakes or natural earthquakes, plate boundaries basically. So with respect to the technical challenge, for hydrothermal, it's really an exploration problem. You have to find a reservoir with a huge thermal anomaly which is flowing at economical rate. So this is really the main. After, for reservoir management, it's mostly hydrothermal, reservoir engineering. You need to do some pressure maintenance in this reservoir. So that's the same in the geyser. We do a lot of pressure maintenance, and that is what has led up to higher actually induced seismicity. And also, you always have to keep in mind in everything related to extracting fluid or at depths, is that at some point, or maybe always actually, you always require a degree of well stimulation. So for example, in Saudi Arabia in 2014, you remember they tried to keep the US shale gas market by increasing their production dramatically. And at the time I was working for Schlumberger, and they were transferring people from the US to Saudi Arabia to do hydraulic fracturing, not in the US, but in Saudi Arabia. Because Saudi Arabia wanted to increase the production rate, even if the reservoirs are very permeable over there, they needed to do hydraulic fracturing to speed up and try to flood the world with cheap oil that they have. So EGS, if you go deeper, or if you have the view that was saying, okay, trying to say that I don't want to do exploration, I want to go deep enough so that it's hot, and then I'm going to engineer my reservoir. The drilling cost and the drilling problems are higher because if you go deeper, a well which go 4-5K, it's usually much more expensive to drill than because you enter also the crystalline basement. You always gonna have the problem of the well stimulation, which is becoming more critical, and lots of the case I would argue it's kind of performed a bit blindly or without much concept behind. Related to it, the problem of induced seismicity. And also something that I've noticed, coming from oil and gas, is that some of these projects, they really run on a very cheap budget. They have a very little amount of money, and that has a direct consequence on some of their choice, because they try to cut down on some important characterization techniques or some type of operations, and that increases their risk dramatically as a result as well. So it's kind of a feedback loop sometimes. So I'm going to discuss stimulation mostly, okay, well stimulation, and I'm going to talk a bit about relate to what Jean has said on induced seismicity. So I'm going to try to talk about two fluid-driven fractures, which are completely different families, and try to highlight why they are so different. The first one is a tensile hydraulic fractures. Basically, the fluid pressure is larger than a minimum stress. And the fluid-driven frictional rupture, where the fluid pressure is lower than the minimum in situ stress. Of course, I can talk for years on these two, so I'll try to limit myself. Try to highlight two things. In the two cases, now we start to have an understanding of what I call propagation regimes. So it's widely different behavior of these two types of fractures depending on the configuration. So the parameter of the problem, basically. For hydraulic fracturing, where the models and their understanding of the process is much more mature than the class on the right, I'll talk a bit about the history of the models, verification against experiments, to try to convince you that you kind of understand the physics of what's going on here. Here I'm gonna lay out what I would say the basic 101 model for this class of rupture, their propagation regime, and I'm gonna discuss a recent study we did about what happened after shutting. Okay? The fact that the ruptures keep going on when you stop injecting. And I'll touch a little bit on the nucleation of frictional instability. So we have to keep in mind what we want to achieve. So is extract or inject fluid at depths from porous rocks, which usually have pores, but they also have fractures at multiple scales. And we want to do that in a safe, sustainable, economically viable manner. So typically, there's a bunch of well completion techniques that people use. The simplest one is this one, that is vertical well. They put casing at a given depth, and then they drive what is called sometimes a barefoot completion or open hole completion, which is just you drill further the well, and you produce from this place, so directly from the rock. In the oil and gas industry, for instance, this is never used, okay, because it's prone to a lot of problems in the long term. So what people do, they sometimes is they want to keep not cement. They use what is called a sand screen, so this type of system, which is basically steel tubular with holes, okay, and they pack the annulus between this steel tubular and the formation with a gravel pack with a very high permeability sand, and they're going to produce from this long interval like that. So, for example, this type of completion it's also used in the Middle East in very permeable reservoir. But I would say probably 80% of the industry is using what is called case cemented and perforated completions. So you would cement your production interval with a casing tubular and cement, and then you come with a perforation gun and you perforate at given locations. Why they do that is because by doing that you control exactly where you're producing fluid from or where you're injecting fluid. Okay. So that's what it's on. So now just a bit about what was discussed before is okay. You can do flow in porous media. This is the simplest configuration you can think of. You know, you all did that in hydrogeology. It's a test solution, so vertical well. The aquifer is confined, and you inject or you produce from this well, and you can solve the problem in polar coordinates. And you get a relationship between the variation of pressure with respect to the variation pressure as function of the rate, the permeability of the medium, the height of the reservoir, the viscosity of the fluid, and you've got this exponential integral function, which you have this diffusive variable. Okay, the radius, the distance, in 4CT is the diffusion line scale, C is the diffusivity of the hydraulic diffusivity of the rock mass. Okay, so you have a self-similar solution for the pressure, which extend in time as a square root of time. Okay, and so here you have the full solution, and you can have what is called a pseudo steady state approximation, which is the blue line here, which is a log. Okay. So you can typically what reservoir engineers do, they rewrite it in terms of a log, and you have the pressure at the well minus the virgin pore pressure related to this. So the rate, the viscosity, permeability, and you've got a log of the radius of influence, RV, which is function of time, which is going as square root of 4CT with time, and the radius of the well. And okay, so why do they do that? Because at the end they are engineers, so all they care about is what is referred to as the inflow performance relation, or sometimes the productivity index, or that's what Jean was showing you. So it has a weird unit. You sometimes, well, there's different way of looking at it, but basically it's the ratio of the rate divided by the wellbore pressure minus the virgin pore pressure. So it's a measure of how easy it is to inject or how easy it is to extract. You know, and the rest you throw it to the bin. Okay, that's what the engineer wants. And he wants this to be as high as possible. So he wants to minimize this pressure drop and maximize his flow rate. So he wants this guy to be big, whatever happens. So you can express this. This is, you know, you divide Q by that, so it's 1 minus this. And the problem is that when you do well bore, usually you find out that, okay, maybe you did some well test and you get this, but it's not quite that. You always have a zone of lower permeability close to your wellbore. And in the terminology of reservoir engineering, it's called skin or formation damage. So basically it's due to drilling mud invasion. Maybe the drillers, they didn't want to care at all, and it happens a lot, so they inject lots of barite or fibers to plug the well because they don't want to lose fluid when they're drilling. But then this is basically plugging all your near wellbore permeability, so you have to somehow reconnect the reservoir. It can be cement invasion, can be a bunch of things. And so that causes like a skin effect. It's a pressure drop flux relationship that people write like that with a dimensionless number S, which is the skin factor. And this skin factor, there's plenty of physics that goes in. So what people do is they do a well test to get it. Okay, they're not trying to predict it. You just measure it. And what happens actually if you take this additional pressure drop on top of the previous one, you can rewrite what I had before. It's exactly the same with the log, except that you have the R prime. So it's like the radius of the well has decreased by an exponential. Okay, so exponential minus S. So this basically, if you have a skin which reduces the permeability, it's like you have a smaller wellbore. Okay. So in practice, you want to improve that. You want to get rid of it. So what people do is a bunch of stimulation. That's good. So acid injection is one which is quite typical to try to get rid of the mud invasion or fibers. But okay, you did that, good. Maybe you regain your initial permeability, but you're still not very happy. It would be great to get a negative skin, because if the S would be negative, then you have an exponential of something which will be positive, and then your wellbore radius is much larger, so you can increase your inflow performance relation. So to do that, they do hydraulic fracturing. Okay, and that's the idea behind hydraulic fracturing. It's linked into this parameter, which is called a dimensionless fracture conductivity. So it's basically Kf is the fracture permeability, W is the width. So Kf times W, it's like your hydraulic transmissibility, you know, in context of flow in fractured media. And it's divided by K, which is the rock virgin permeability, time XF. XF is basically the length of the hydraulic fractures which connect to the wellbore. So it's a ratio of the two that's going to control your increase on your flow pattern around the well. So as you start to produce or inject from an hydraulic fractured well, you go into a sequence of flow pattern for a simple case here. So at the beginning you have a linear flow, so the flow is only in the fracture. Then you start to connect with the reservoir, so you have bilinear flow. Then at some point you reach to that stage where you have a formation linear flow, and then in a fracture it's like a highway, so the fracture flow is very, very fast. So that's the case of very tight formation. So if you think of shale gas, that's the kind of state they're in most of the time. And if the time goes on, you get elliptical flow, and at the very end you get a pseudo-radial flow with an equivalent wellbore radius, which is much larger than the your well. So that's the idea of the negative skin. So you can quantify that. I'm not going to go into the details, but for simple flow patterns, you get this increase of the wellbore radius, okay, as function of this dimensionless fracture conductivity, okay, and so it's scaled with the length of the fracture. So the length of the fracture plays a role, the permeability of the fracture plays a role, and its thickness as well. So just to give two examples, the guys in the industry, they like to talk about fold of increase, so how much I've increased with a particular stimulation. So this is an example of a formation which is rather low permeability, so 5 microdarcy, so it's not that tight, but it's kind of tight. And you see the fold of increase as function of the length of the half length of the hydraulic fractures and the permeability of the hydraulic fractures. You see changing the permeability of the hydraulic fractures basically don't change anything in that case. You go nearly linear at some point, so it's really a function of the length of the fracture. And that's the case for very tight formations. It's really controlled by the fracture length. You need a bit of fracture conductivity, but the key point is the fracture length. If you switch to a higher permeability reservoir, so 0.1 millidarcy, so now you're in like in Saudi Arabia now, and you see that now the picture is a bit different, because at some point, for a given fracture conductivity, like this one, so which is the lowest one, if you increase your fracture, you don't gain much in terms of fold of increase. So a short fracture can already do a lot. in that case. But you need to do a fracture which is high permeability, okay? Higher than the rock. Okay? So that's where you need to really have propant and pack of propant, which is very good. So hydraulic fracturing, in simple terms, it's an engineering technique to get a permeable channel from a web in order to improve its productivity. You have a very high quantitative channels. So in a sense, you inject a volume of fluid and you will transfer it to a surface area. Okay. And if you only have a technical, let's say, your inflow performance relation, you can have a multiple solution for it. Okay. You can have a short fracture, long fractures. You can have different optimum. And so it's only by taking into account the project economics, that you can get, an optimal point for the net present value of the cost. So it's been around for a long time. That's a picture I like to show sometimes. This is taken in the 1950s, where you see these very clever engineers with this notepad. It's gonna solve all your problems. It could be the best treatment for you. So that's from Schumberger in the 50s. And you know what? This kind of treatment, it's actually very, very similar to what they pump today in unconventional gas in the US. They did it in the 50s, but they kind of abandoned it because the reservoir of shale or the drilling costs were too large and everything. So they went to more polymer treatment with lower number of trucks, but they went back to it in the 90s. So it's interesting. I'm not going to go into the details of the engineering, but just for you to keep in mind that it's not only a mechanical problem, and by far it's mostly chemistry actually. So it's not so much about wet mechanics in practice. What do they do? So okay, that's a very simple schematic for a given vertical well. First of all, what you say in the jargon of the industry, you break the formation. So you break down the formation with a fluid pad. So usually it's a relatively clean fluid, low viscosity, no solid in it. And you break down, you see that the pressure starts to decrease while you're injecting, which means that it's like a stress strain curve. You pass the softening peak, so you have a fracture. And you're propagating the fracture. Then you switch to more viscous fluid in order to increase the aperture of the fracture and to be able to inject sand. So then you inject sand. That's the yellow, okay. And then at some point you shut in, so you stop pumping. You may or may not flush. So sometimes sometimes they stop pumping the sand before stopping pumping the fluid, such that they don't have any sand in the wellbore. It's not necessarily a good idea because if you flush too much, this sand patch will move away in the formation, and then your fracture will close near the well, and you have lost all your wells, basically. So sometimes it's better to actually leave a little bit of sand in the well. And then they let the fracture close. It can take a while in some very tight formations, but it will eventually close. And that's why you put sand, because if you don't put sand, you don't produce. And after you do a phase which is called the cleanup, so there's lots of chemistry of the fluid in order to degrade the viscosity and extract basically the fluid that you've injected into the fracture so that you can produce from the reservoir without any chemistry. Okay. So it's a technique which is used a lot of course in oil and gas, but in some of these hydrothermal, geothermal projects, they also do it just because to improve the well productivity, just as simple as that. Let's talk a bit difference between what it is and what is referred to as hydro shearing. In geothermal communities, they talk a lot about hydro shearing. So in the 70s in Phantom Hill, they tried hydraulic fracturing. Didn't work there. Okay, we can go back and discuss why it probably didn't work there. And then they had a kind of a consensus that built up over the 80s, 90s that hydro shearing should be the way to stimulate a geothermal reservoir. But the mechanics is very different, so I think it's important to discuss it. So in rocks, there's spore and fracture. So within the concept maybe of geothermal, of crystalline rock, where you have a fracture system, one thing that I think Jean mentioned is, I mean, exploration and knowledge of this and the fluid flow in this is very, very critical before doing anything. But one thing you have to keep in mind is that with most of the geophysical techniques, you can get very well. If you do your job right, you can get the orientation statistics, some of the width statistics with some well logs, but the length and the shape of the fractures is really, really poorly constrained. And that has consequences on the amount of deformation you get. So we know, okay, it's always going to localize the deformation in geomaterials. So to my opinion, you might as well recognize that and just put fracture to start with. It will save you some time. And so the 4 level of pressure, so that's concept that François Cornet also liked to present a lot. So the first one is you have defect in your material, so you're gonna, by increasing the pore pressure, you're gonna have some of these favorably oriented defects that they're gonna start to pop up. You increase the pressure, the large one may really, really pop up. So that's the example of a fault, basically. And if you continue, you will create fresh shear fractures combined. So that's going to be like a mixed mode combination of linking existing fractures with some shear fractures. And if you have even higher pressure, then what happens is that actually the mode of fracture completely shifts and you got hydraulic fractures. So that's an example of an hydraulic fracture experiment where you see a discontinuity that is building up, which is perpendicular to the minimum stress applied, and the fluid pressure is larger than the minimum stress. So you get purely tensile hydraulic fractures. So if you look at a sketch of this cartoonish fracture growth mass, at the beginning, okay, you inject, you may have some which activate in shear, or maybe not even. You may just diffuse as the fluid flow in there. And then at some point, you're going to have a linkage, and you see basically the orientation of a shear band of the pre-existing fractures arriving, so which is inclined with respect to the in situ stress. And if you inject at very high pressure, you will eventually get another fractures. That, of course, if there is pre-existing discontinuity, it's going to be affected by it. Okay, it's not going to be a purely tensile fractures if you have discontinuities around. Hydro-shearing, it's this idea. The idea that when you're going to shear slip, you have asperities, example of fractures from the lab, and you're going to dilate. And so by dilating, you're going to increase your permeability. So 2 things to keep in mind. The notion of critical state. So if you remember your some mechanics class, you take a loose pack or a dense pack, you shear it, you eventually reach a critical state where the shear dense is built up and you don't have any variation of volume. The same actually happens in rocks, but in rocks usually the samples are too small compared to the typical lab experiments apparatus. So you never quite see the deformation going all the way to critical state in rock because it would take a metric scale deformation to see it, but it will eventually get there. So people also, there's few tests published on fractures in granite at different level of stress, which look at the dilatancy angle as function of the accumulated shear slip. So you see that the dilatancy angle as the slip builds up is going to 0. So at some point you're going to cap off the dilatancy. Okay? So dilatancy is always going to be capped off. And it's a classical nature of geomaterials. They go to a critical state where at some point you don't have any dilatancy occurring. So it's very important to keep in mind. And honestly, you cannot engineer that. This is what's going to be given to you by your mass and the fractures. So if you think of hydro shearing, you don't have a lot of leverage. You just have to live with what you have. So in summary of this, I call this one lifting the chair, and the other one is dragging the chair. Guess which is the one who is making the most noise? You can imagine it's this one. Also, maybe another point is regarding when do you see order? Do you have can you use continuum mechanics in this or not? So my argument is yes, at some point you can always use continuum mechanics. Of course, if you're in between scales and you're gonna have lots of fluctuation, you have to realize it. But as I will show later, actually it's if you keep injecting, you're going to have a seismic slip, and the seismic slip will be also in scope of time. And you see, at some point you're going to see order building up. But it really depends on the statistic of the rock mass and how much you inject for how long. Recently, we did some simulation with a student on this kind of setup. So you have a discrete fracture network. This one is initially relatively close to failure. You inject into it, and you see in red the cascade of activation of slip. Okay. And actually, in this case, the pore pressure disturbance remains extremely limited close to the wellbore. It's a case where it's really stress transfer due to the accumulated slip that builds up. And when you do the statistic of the fracture which pops up, most of them are critically oriented in the favorable orientation of what you expect, knowing the friction coefficient of this. And actually, when you plot after the injected volume with respect to the aseismic moment, what you get is, in fact, it's exactly the case of a single fracture. So in that limit, you don't even care anymore about the statistics of the network because it's given by stress transfer and by preferred orientation. This is completely different in the other limit, the marginally pressurized case. So I will come back to that later. A bit on now the hydraulic fracture first, and then I'll move to the fluid drain fractures. So in a nutshell, if there is only one slide that you need to know about hydraulic fracture, it's this one. So you have a very complex, intricate nonlinear problem actually, because you have solid deformations. Okay. You have fracture surface creation, so it's a linear elastic fracture mechanics. If you assume linear elastic fracture mechanics, and then you have flow in that fracture which is open. Okay, so fluid flow. And as you can imagine, it's highly nonlinear with the pressure because the pressure increases the width of the fracture. In the lubrication, the flow is going to be a function of the cube of the width, so it's extremely stiff. And it's a moving boundary value problem. You don't know the velocity of your fracture tip, okay? And it depends on the overall dynamics of the problem. You have two things which balance. So first of all, your mass balance. As you can imagine, you inject fluid. It can be stored in the fracture, so it can be basically used to just propagate the fracture, and this is why the process is so efficient. If you're in a very tight rock, it will mostly remain in the fracture. And the second term is leak-off. So leak-off, this is a small arrow here, is the fact that the fluid is at a pressure which is usually larger than the pore pressure of the rock, so it's going to leak off, and you're going to lose fluid in your matrix. Okay. So you have this mass balance. So you can have situation where storage dominates, you can have situation where leak-off dominates, and the dynamics of the fracture are completely different in the two cases. Then you have the energy balance. So your energy input, which is your pump rate and your fluid pressure, is going to be balanced by a series of terms. So okay, you're going to store energy elastically in the rock. You're going to have to work against the in situ stress. So sigma 0 is like my sigma 3. Okay, it's my minimum compressive in situ stress. So this term is the highest of all. So if you want to, the guy, if you go to someone in West Texas or wherever, and he wants to design a fracturing treatment, the only thing he wants to know is the stress, because he can compute that term, and then he knows how many number of trucks he can bring on site. The rest is peanuts. Basically, it's irrelevant. So that's the test of mechanics that I learned to my dismay. But basically, this is all. If you get that, you can design the treatment. Then you have dissipation. So nevertheless, these dissipation are very important. Okay. The first one is the fracture mechanics dissipation. Okay, you create fracture surfaces, so you spend energy in doing that. And then you have viscous dissipation. So viscous flow inside the newly created fractures, but you have also viscous flow due to leak-off. Okay, you lose energy in that. And also viscous flow down the wellbore. This is again one of the dominant terms. So if I want to go to second order for practical stuff, I just compute the wellbore, and I still don't do any fracture mechanics. And then you have also viscous drop in the perforation. But after, for the propagation of the hydraulic fractures, the competition is between the fracture creation and the viscous flow in the fracture. And depending again on some case, which, okay, it depends on the material parameter, on the way you inject, one can win or the other. And the result is that the propagation of the fracture is very different in terms of velocity, in terms of aperture, in terms of pressure. So in the past 20 years, there's been lots of work on basically getting a good knowledge of this, let's say, not triangle, but quadrilateral between having storage domination with viscous, or storage with toughness, or leak-off with viscous, or leak-off with toughness. Okay. And the way the fracture propagates is quite different. Maybe it's too late for a question, so I'm not going to go too much into this. I can go back if you want. Just to tell again, it's quite a nonlinear couple problems. You want to solve for the net pressure, the fracture opening with time, and the fracture velocity. Okay, you don't know the fracture velocity. This is part of the problem. Maybe to have a handle of the different regime, you can look at a simple case of the radial fractures from the wellbore. And you can show in the case where leak-off is minimal, so that the storage dominated case. At early time, most of the dissipation is occurring in viscous flow because the perimeter of the fracture is small. So your fracture mechanics increments, you're going to have GC times the perimeter times dr. So actually, if the perimeter is small, the energy spent in creating new fracture surface is small. Okay, so it's not the dominant term. Whereas when the fracture is large, you have a large radius. So to do a delta R, you increase a lot the fracture area. So that becomes dominant now. So you have a time scale to shift from viscosity dominated regime to toughness dominated regime. So the power law of growth are different. I'm not showing them here, but the time scale of transition is depending on the viscosity of the fluid, the rate at which you inject, the moduli of the rock, the fracture toughness of the rock. Then you plug numbers for some different treatments in a typical rock, okay, if there is anything such that a typical rock. And what you found out is that for gel, it could take 10 to the power 5 hours to reach to the toughness dominated regime. And for slick water, what they call slick water, or water with some little bit of chemical, this is actually the viscosity of water I took here, it's 2,000 hours. In most cases, they inject for 45 minutes. So you can see that they don't even know what fracture toughness is, for a very good reason, because they don't care. So in energy, most of the energy spent in viscous dissipation in fracture practice. But it's not always the case, but in lots of cases it's like that. After you can do things a bit better. I'm not going to enter into everything, but for that radial fractures, you can compute the different energy terms, which are computed here. And you see that at the beginning, so you have basically the energy stored in the medium is following at the beginning the one dissipated in the viscous flow, and at the end the one in the fracture energy. So you have a transfer of viscous energy to fracture energy, and this is stored elastically in the rock, okay, as you go. So with time, you have this change between viscous behavior to toughness behavior. Some history of models. So in the early 50s, or let's say end of the 50s, people started to look at plane strain model. They called the KGD crack. For the guy who did it, it's Kristianovic, Gaznat, and Ecole. And basically, it's like infinite extent, so it's plane strain, it's 1D crack. It's basically useless for any practical purposes because I've never seen in the Earth plane strain fractures. After people have observed that actually the fractures, they remain quite contained in some layers. So they developed a model where the cross-section is like a Griffith crack, and then it extends in the propagation direction like that. And so the pressure will be uniform at every cross-section, but it will be different along the propagation of the fracture. These models are modeling the fracture like a finger or a blade. So they have also a weird name from the guys who developed it. So that's the other. Then these models were extended to what is called pseudo 3D in the 70s, basically to allow for the fact that the fracture may break in the top or bottom layers. But this model of pseudo 3D is kind of mathematically imposed, so it causes lots of problems. So after, people have moved to planar 3D or full 3D models. Another type of solution that exists analytically is this radial fracture, which is very useful because you can benchmark a numerical code. It's fully 3D, so it's quite useful for this. And actually, it's a geometry which is relatively relevant in the early time where you can assume the medium is homogeneous. So after, for planar 3D growth, so I'm not gonna, if you're interested, I can discuss for hours about how you solve these problems, but now we have relatively robust solvers to do that. And so we have one in my lab. It's open source if you want to try it out. But basically, this is a sketch of an experiment, and I'm going to show you experiments after in the next slide, that was done in CSIRO to test how the hydraulic fractures is affected by jump in stresses. So they manufactured, and it took say 5 years to find out how to do that, but to have the initiation in a given layer of stress, then at top it's a higher stress field, and at the bottom it's a lower stress field. So the fracture would tend to grow in the lower stress field. And you have here in black the experiments that were done in PMMA, so they could really see the fracture front. And you have in magenta the prediction of the model. So there's no fit in that, it's just prediction of the model. So after, you can do plenty of different things with this kind of code. So recently we played with magmatic intrusion in the earth. So you see this buoyant hydraulic fractures that grows, that reach a zone where usually you have the density contrast the swap, and you elongate. So that's also some interesting beast. So it's not related at all to well stimulation, but this also occurs naturally in nature. Going back to what is interesting more for hydraulic stimulation is this, the fact that you have change of properties in the earth due to layering. And people observed, when they do hydraulic fracture in coal bed. So this is the thickness of the coal layer that was stimulated with an hydraulic fracture, which is, you see the sand is fit there. And you see at the top and the bottom, you have basically debonding of the interface between the shell and the coal. So it's like an edge fracture. They call it sometimes T-shape because they just look at the top, T, like that. That's a case of a dike which is crossing all these layers. So this magmatic intrusion in nature, the geologists can go and map them out. So this is crossing everything, and this is a case where it arrests when it reaches another localization. So you can have arrest or crossing depending. And what people have found out is to the first order, so stress, variation of in situ stress is what is controlling. Of course, you can think of material properties change. So that's the two. A good experiment that was done in CSIRO was this one. So it's the same setup than before, but here I'm going to show you just more data of it. So this is the central layer with the lower stress and the magenta layer of higher stress. So the fractures initiated here, propagated in a radial way, and then got contained. So here, at a given time, you have basically with optical measurements, they were able to measure the width of the fracture. So you see at a given time, the red dots are the width of the fracture in space, and the model prediction is a continuous line. So you see it works relatively well. And after a while, it breaks through, so you have a little bit of mismatch just after breakthrough, but not too much. In terms of fracture footprint, it's relatively good. So you see the continuous line in black is a model prediction, and on the red dots is the actual measurement of the front. So it's matching pretty well without any. So it's just a prediction. It's not. There's no parameter which are adjusted whatsoever. And that's in time, the free pressure, the fracture opening at a given point, the fracture half length, that for actually different experiments in that case. So that's the stress contrast is the first order mechanism that contains these fractures at depth. And that's important because there's always the fear that they run away. Okay? And so that's characterizing the stress contrast is what people do in the first place to know if it's going to be problematic to do any of this kind of injection or not. Then there are other mechanisms that can play. So we looked recently at the case of a layering of fracture energy. So just a change of fracture energy. So a layering of the Earth with a K1C1, which is in white, and a K1C2, which is larger than K1C1. But larger, not much larger. 1.3, 1.4 is enough. So you get contact. So of course you have to be in a toughness dominated regime because if you're viscous, you don't feel the toughness. Okay. So but at some point you're going to get toughness dominated. You get contained, and you at some point slowly break in the layer with higher toughness, top and bottom. And at some point when you really go to the lower toughness, then you accelerate. And you catch up back to an elongated fractures. And this repeats. So then you propagate like this for a while. You reach the pressure here re-increase because the fracture gets contained. And you're gonna re-break through in the top, bottom, tougher layers. You accelerate in the lower toughness layers, and you repeat like that. So this is a sequence that repeats, and it's all at each time it's increasing the aspect ratio of the fractures. So again, the material heterogeneity like toughness, but the same is for Young modulus, is also playing a role in confining these fractures at depth. Anisotropy also is a mechanism for that. I don't think I have time to present it, so I will skip it. But just to tell you that intrinsic anisotropy is also something that is containing these fractures at depth. So for hydraulic fractures, the main risk is this, the height control growth. Okay. There is something that I didn't discuss, is induced seismicity. Hydraulic fractures are mostly aseismic. The only problem is that if they hit a fault. Okay. And if they hit a fault, then big stuff can happen. There's not a lot of many examples of that, but there is maybe 10, I think, well-documented example of an hydraulic fracture hitting a fault, pressurizing it with an earthquake. Okay. And there is one which is extremely nice in Canada. If you're interested, we can talk about it. But it's a case where basically the fault was creeping in a shell layer due to geological tectonic stress. And the fact that the hydraulic fracture hit the fault accelerated the seismic slip. That was transferred to the carbonate layer, which was above, which was frictional weakening, and a magnitude, I don't remember, 3.7 or something like this, nucleated in the carbonate. So, hydraulic fractures, if they hit a fault, it can be pretty bad. But if they are in homogeneous media, they are relatively aseismic type of rupture. So now if we look at the other class, so the one where the field pressure is smaller than sigma 3. So we think, okay, of injecting into fault zones, well, something that I will not recommend, but some people think of this, but fault zone or faults, they are very complex. And of course, as engineer, we kind of simplified everything in a plane. We do that because, model, it's always a simplification, so we might as well go for it. And after, you need to do a model with a purpose or a specific task. And here, what we are trying to understand is basically by injecting, okay, we're going to eventually trigger more coulomb failure. It's going to be a frictional crack, but now how this frictional crack is evolving with time, how it is growing with time, if we keep on the injection. Let me go maybe to this. So we'll have pore pressure increase, we'll have a seismic slip stress change, and we want to understand the coupling between the two and how they occur. Something also which people start to realize now, and I think the example that Jean showed about the Soultz-La-Forêt well, where François Cornet was really the first one to show a seismic slip in this deep well. It was there's also observation in mines before that, but I would argue most of the slip is actually aseismic, frictional slip is aseismic. So with that in mind, we built a model which has very strong assumptions, but we try after to solve it. So we're going to look at the pulse injection. I'm going to first talk about the stage where we continuously inject, and then I will talk about what happened after shutting. So we have a fault or fractures, which is a scene interface. We're going to assume that its hydraulic properties are uniform and they will not change with slip, which is an assumption I recognize, but it's the first one we did. Then we say, okay, the rock mass is elastic. We assume there's no fluid leak off from this interface to the host rock. Okay, so the time scale of injection is much smaller than the diffusion time scale of the rock. We assume like a point injection or a line injection, in that. So we just inject directly in the middle of this pre-existing crack. And then we assume just more Coulomb with a constant friction. And the stress initially we take them uniform. So we're going to have something like that. In red is the rupture radius. And in this bluish color, you have the pore pressure diffusion front. So we are after how the frictional rupture front is evolving with time, and then how the slip and the slip rate are developing in the rupture patch. So that's okay. The equations we solve. So the elastic balance of momentum, we can recast it as Bondel integral equation, whatever. You can solve it in any way you want. The Coulomb frictional failure. So the strength of this interface is F. So this friction coefficient F that we assume constant. Sigma prime 0 is the initial, normal effective stress. So sigma 0 here is the normal effective. The sigma prime 0 is the normal effective stress. And we have a delta P due to the injection. So the delta P due to the injection here is actually exactly the one that I used before. It's an exponential integral, but now the Kw is a fracture permeability, the fracture transmissibility. Okay. And so the rate, we're going to first look at the case where the rate is uniform, constant. Numerical method, I'm not going to talk about it. If you're interested, you can ask me questions after that. Actually, the details are in that paper. But now let's look at the physics and what is important to recognize. You can do the scaling analysis of that problem, and you can find that it's a function of two parameters, two-dimensional parameters. The first one is the Poisson's ratio. And the Poisson's ratio is basically going to tell you if your rupture is circular or if it's elongated. Then the one which is more important, is this T parameter. We call it the stress injection parameter. So it's a ratio of F sigma prime 0. So that's the initial strength of the fault. Tau 0 is the initial shear stress on the fault. So the difference F sigma prime 0 minus Tau 0, this is a distance to failure. So before you inject, are you close to failing or not? That's what it captures. And then at the bottom here, you got F times delta P star. So F is again the friction coefficient, and delta P star is the strength of the injection. So why F delta P star? Because you basically decrease the strength by F delta P star. Okay, and this basically governs everything of the system. So it's the stress test before you inject and the strength of the injection. So you can take two examples. Initially, you are 3 megapascal away from failure, so your fracture or your fault is quite stable, but you inject like a maniac, and you have F delta P star of 30 MPa, and then you have a T of 0.1. Or you can view the case where you are quite close to failure, 0.3 megapascal, but you inject at a lower rate, and the pressure builds up, characteristic pressure buildup is less, 3 MPa, and you get also a T equals 0.1. So in that case, the two systems will respond exactly the same, even though your injection and your stress are different. So there's two limiting values. The first one, when T is very, very small. So T very, very small, that means that your distance to failure is either very small or your strength of injection is very, very large. If it's that case, we call that case critically stressed. Okay? So critically stressed, meaning it can be either the distance to failure or the injection. Or if T is very, very large, then we call marginally pressurized. Okay. So these two regimes, they were already laid out in the literature in different places, but now they are really well captured with this map. So there is also the effect of quotient ratio. I'm not going to discuss it too much, but basically the nice thing is that when the quotient ratio is 0, the ruptures are circular, so it simplified your life. Of course, nobody knows the quotient ratio 0, but the effect of quotient ratio is actually relatively minor, as I can show you. So then you can do, in the case of circular rupture, you can recast the problem and solve it semi-analytically. And it's a self-similar problem. You can show that the rupture radius divided by the diffusion length scale. So the diffusion length scale is the square root of 4 alpha t. Alpha is the hydraulic diffusivity of your fracture. So this is the fact that the pore pressure front is moving in a diffusive way. Okay. And lambda is what we call the amplification factor. So R is the rupture radius and L is the pore pressure disturbance radius. And you get lambda as function of T. Okay? So either lambda larger than 1 or lambda greater than 1. And the solution is like that. You have these two regimes. So the marginally pressurized regime, lambda is very, very small. That means that the rupture radius is much lower than the pore pressure disturbance. So you have a little bit of frictional slip at the injection point, but most of it is large-scale pore pressure diffusion. That's that regime. Okay, here. Or you have the other way around, critically stressed. You have a very, very small pore pressure disturbance, and the rupture front is way ahead. This is this limit here, okay, where you have very large lambda. So after you can get also scaling for the moment, the slip profiles, which are very different in the critically stressed or in the marginally pressurized case. Okay, and as a result, also the seismic moment. I'm not going to go into that. But if you put the quotient ratio different than 0, you get elongated rupture. So that's an example for mu equals 0.3, but for different value of T. So that's marginally pressurized. As you can anticipate, marginally pressurized, it's really the pore pressure that governs, so the rupture is more circular. And critically stressed, the rupture is more elongated. It's more stress transfer and elasticity that governs than pore pressure in that case. So after you got this, we got this diagram for the quotient ratio and the aspect ratio in the two cases. So that's the case of constant friction. So usually after the geophysicists they say, oh, but the friction is not constant. Actually, yes, but we argue that actually you can show that when the rupture is going, maybe like in fracture mechanics for shear, you may have some rate and state effect or things related close to the fracture tip, okay? And you may have now an equivalent fracture mechanics energy. And if the crack is long enough, this effect is going to be small compared to the frictional effect along the remaining part of the area of the crack. So at large time, we can neglect the fracture energy, and the solution for constant friction is pretty good. With the value of the friction coefficient, you should take the residual friction. Now maybe I'll talk a bit on what happens after shutting. So we did the same, but now we stopped the injection at TS. So that's the only difference. So the simple way to view it is like this. So when you inject, the rupture is constantly expanding. It's like a crack. But when you stop injecting, the pressure at the well will start to drop, and you will relock. So you relock the fault, close to your injection, and you have a back front, okay, where the fault basically gets relocked, that is propagating. So you have like a pulse, and the rupture is still evolving with time, but as a pulse. So before, so you have, if you view it in time, so we plot here a normalized time, so with respect to the shut-in time, the moment at which you stop pumping, and we have the front radius divided by the radius at shut-in. So you see that at shut-in it's 1, but you keep propagating after shut-in, and you have a locking front that starts immediately at shut-in, and is going faster than the rupture front, and at some point they catch up, and the fracture arrests. You have coalescence of the two front, and the fracture arrest. So you arrest at that moment, which is the time of arrest. So you see in that example, it's 7 times the times of the duration of the injection. And you got a final rupture radius of 40%, close to 40% larger than the time of rupture at the moment when you stop the injection. So after, you can show that in that problem, so pending the small effect of the quotient ratio, the time of arrest and the radius of arrest is really a function of this T parameter, okay? Which is the same than before, with these two regimes, critically stressed, marginally pressurized. So then after we span the system for this, so the stress injection parameter, so when it's larger than or close to 10, here it's marginally pressurized. This is the normalized arrest time. So you see when you are marginally pressurized, you stop injecting, and the rupture stops immediately. You don't have any more additional growth because you are far from failure initially, so you stop immediately. But on the other end, starting relatively for T 0.5, you have a regime where you have time of arrest which is increasing a lot as you decrease the stress injection parameter. So as you get more critically stressed, you see you can go to cases 0.01, which is like 500 times the injection period, or even 1,000 times the injection period. So that the rupture is going to keep going for a very, very long time. And for the radius of arrest, compared to the radius at shut-in, you see a more gradual transition. So in that zone, you immediately arrest, so it's 1. That's basically a safe domain. And here it goes on for a very long time. So you have, you can go to not quite 2, but 1.6 at values of T which are very realistic. So it tells you that it's not going to be the end if you stop injecting. And that's, kind of rings a bell with a lot of cases where people have seen that even after shutting, sometimes that's where the largest induced events occur. So here everything is aseismic in the model. There is no notion of instability that we have accounted for. But you can think of, okay, here we are perturbing the stress as the rupture is getting larger to a larger domain, and that can promote seismicity on a stress transfer on a much larger scale. So that could induce some seismic event by having a larger propensity of perturbing the stress in a further distance. So that's the SULES GPT-1. So Alexis then looked at this case because from the measurement of the slip at the wellbore, you can constrain the hydraulic diffusivity, not from an hydraulic test. So we use that to constrain the hydraulic diffusivity, and the delta P star, you had to express it. It took basically the average of the volume over the duration of the injection to get a rate which was an average rate. And you have here in black that's the rupture radius prediction. and the clouds as like Shapiro plots it as function of the distance from the injection point and at the time from the start of injection. The shutting is here, and in red is this locking front that Alexis predicted from this. One thing in terms of mechanics which is interesting is that there is a pore pressure back front. So the peak of pore pressure now is not at the wellbore anymore, it's traveling inside the medium and it's decaying. Okay? And at some point this pore pressure back front is merging with the locking front and the arrest of the rupture. So basically here we see that the rupture is still going on quite a long time, for quite some days after the arrest. So you have more details in that recent paper for this. And then he looked also briefly at the Richtershofen injection. So here I think the constraints are not as one would like. There is more unknown. But they were seeing some seismicity on. So they were first seeing seismicity on a fault close by the injection, and then after the shutting, some small swarm, so relatively low events, occurred on another segment. And by stress transfer, you can explain that. So computing the Coulomb stress change, 4 days after shutting, you could see that it's there's not a lot of difference between right before shutting and 4 days after shutting, but it's full. It's a plausible explanation for this. And I will conclude on the shear crack by just saying that when you compare to hydraulic fracturing, we are in a state where we have the first models. They look to provide a realistic answer, or at least something that physically tells us that it makes sense, but we don't have control. I would say control observation. From field cases, it's always very difficult to. I'm not claiming that the model is verified because there is so many ways in a field test that could explain the same response that you have to be very careful. What we need to do now is very controlled lab experiments in order to see the frictional shear rupture and the pore pressure and try to measure the two in a distinct way. And that is an ongoing work which I think will take a lot of time to be able to do it properly. So I'll conclude by a few things. So the first one relating to hydraulic fracturing or stimulation. Hydraulic stimulation, so the hydro shearing, it really relies on what the rock has in stock for us, because we cannot really engineer the latency. Intrinsically, it's more prone to instability, and you want to stay away from large faults, because that's kind of obvious. The hydraulic fractures, they can be engineered. There's a lot of work, lot of return of experience on that. But you have to stay away from faults, again, because that can be the same problems. But the percentage of problems with hydraulic fractures hitting faults is very little compared to the seismicity in all geothermal projects, actually, if you look into it. The problem is high growth. High growth, actually, you have to control it. You have to do the characterization to ensure that there will be high growth. That will be control of the vertical growth of the fractures. You need monitoring. So in lots of US projects in unconventional, where they are a bit in the attitude of the wild west, they don't like to do lots of measurements. But they still do monitoring at the first few hydraulic fracturing they do in a given place to ensure that they don't have any problem of vertical containment of the fractures. And actually, recently, the EGS people, with the Inflation Reduction Act in the US, they are flooded with money. So you have lots of startups trying a lot of things. So Jean mentioned the Forge project, okay, in Utah. Well, they want actually they want to do hydraulic fracturing or hydro sharing. So they're trying both. They are trying a bit of hydro sharing, but they're also trying hydraulic fracturing with propane. So injecting propane and engineering the fluids for that. They have not yet communicated on the performance of the wells after this treatment, but they are trying to do that. Then there is another company, Fervo, that is going directly commercial scales. And here, these guys are coming from the unconventional gas, and they took everything from unconventional gas. So they say, okay, we're going to do vertical well, then horizontal, and we're going to place 200 fractures with propane. So hydraulic fractures with propane. So they do a treatment the same than the 1950s picture I was showing. So slick water, very large volume, low viscosity with lots of propanes. And so they reported in a paper in the Stanford geothermal workshop this year. They managed to place all the fractures and they get the macro seismicity and everything. The only thing they are not yet reporting is the production rate of the well. But they managed to do it, okay? And a lot of people, I remember also talking to the people of the Hot Sand project 7 years ago. And I was telling them to do hydraulic fracturing and put propanes in it, and they told me, no, you're crazy, it's never gonna work. Well, it's gonna work, I can tell you. And the Americans are gonna make it work. They're gonna spend millions, but they're gonna make it work. And the idea that propanes they will be crushed because the stress is too large, there is a very simple solution. You use bauxite or very expensive propanes, but that are very strong and that don't crush. After, for the chemistry, actually, the chemistry, it's not that complicated to tune for this kind of temperature. And also, these guys, they report that they have found out that you need a lot of hardware. On the way, in Fountain Hill, when they try to do some of this, so the Fountain Hill in the 70s, they tried also to do a horizontal well and to do hydraulic fracturing. But at the time, they didn't have the gear, so the packers failed. They had lots of kind of problems. They could not isolate the well in good portion to do hydraulic fracturing. Here, they have been using exactly the same plug and perforation techniques, so the bridge plug and everything is hardware that they used on the well. They just took the one from unconventional, and because they were either very smart, I think they were probably quite smart, they didn't bought the expensive one that were rated at 200 degrees C, because they found out as we pump fluid, we cool down these plugs, so we don't need to have high temperature plugs. So they're actually using cheap plugs that are rated for 100 degrees C and not 200 degrees C. So we will see if they report on they are successful. But I know that there is a lot of companies in the US that are going that route. I would not be surprised if in 5 or 10 years they are in a place where they can be economically viable. More on the mechanics. So it's this kind of hydromechanical problems with ruptures or moving boundaries are very nonlinear. And I can tell you, I've been trying for 20 years to model them. There's a lot of cases where you get completely crap, and so that's why validation is very important. I would say that now we start to have good numerical scheme, and they start to be relatively well verified, at least for hydraulic fractures, which are the more mature, I would say. The key message is that basically these problems, depending on the conditions, so in situ stress, material properties, the injection, you can have very different response of your system, and they can be in a very different domain. And that's also a challenge for the numerical simulators, because I know, for example, for hydraulic fracturing, it's very easy to do a very good numerical solver for toughness dominated hydraulic fractures, but not viscosity. So it's if you want to have a numerical prediction tool that is robust in a different regime, it's not that trivial. For frictional rupture, we have these two critically stressed marginally pressurized rupture, which also are different. The model that I've shown you, we assume that the slip was not modifying the hydraulic permeability. Also, I mentioned shear dilation. I neglected it. Okay, so you can take into account the shear dilation. It has some effect. But what we see is that basically in the critically stressed, because the rupture radius is much larger than the pore pressure disturbance, the variation of hydraulic properties are not very meaningful to the problem. They are there, but they don't change the response of the system. Whereas in the marginally pressurized, then they are to first order impact because they affect the way the pore pressure zone is actually increasing, which is directly relating the way the rupture is increasing. So in the marginally pressurized frictional rupture, that's where the change of permeability will be playing a role. So hydraulic fractures, they are quite mature. Okay, we don't understand everything, but we have some good match with some data, control data. And I would say that we need the same for this frictional driven rupture. So good lab experiments, not something that you slip 2 centimeters of core, but at least something that you can slip, let's say, 30 centimeters. That would be very good, so that we can have a measure of the frictional front and the pore pressure front at the same time. And that's it. I think I'll stop here if there is any question.
Yes. Thank you for your presentation. How precise do you need to be on the value of T? Because it depends on sigma 0 and tau 0.
Yeah.
They may be very local variables.
Yeah.
So how often do you measure them on the field along the fracturation?
I think so. That's a very good question. I think if you can estimate T, so let's go back to its definition. Yeah, if you can measure T, you're in business in a sense, but it's not easy because okay, the friction coefficient, you can assume it constant and equal to your preferred value, but you need the stress field, and so for that you need to do characterization. After the delta P star, it's really related to the hydraulic properties of your in situ reservoir. So if you do a well test before at low pressure, you can get these values, and then you can estimate delta P star. The real problem is more the in situ stress, like any problem in geomechanics, right? If we know the in situ stress, usually the problem is solved. But it's a measurement of this. And so for that, the fracture orientation, so to measure the stress tensor, if you have, let's assume you can know the fracture orientation. So the key point is to measure the maximum horizontal stress. So the minimum horizontal stress, you can do what is called micro hydraulic fracturing. Some people that just do drilling and they do leak-off test or extended leak-off test, usually that gives you the values of the minimum stress, which is it's an upper bound. But after the problem is really the measurement of the maximum horizontal stress. There are few techniques for that, or you can constrain it with well-bore logging. That's the state of the art, is to try to constrain it with breakouts and combine it with some micro-hydraulic fracturing tests to try to reconstruct your stress tensor. But this is very, very difficult. Well, it requires a lot of work, and it's well spent because, as you can see.
Thank you for the presentation. Can you estimate fraction extent? How far would go the fracture?
So in which case? So in the frictional case, or in the in both cases, that's what we try to predict, right? In the hydraulic fracture case, that show you it's in the lab, we are predicting very well the experiments.
Good.
For the frictional case, we don't have lab experiments, so I will not claim we predict anything. But and when you look at the salts case, we didn't tweak. You know. The only things we tweaked was really the hydraulic diffusivity, and it's at the end it's very similar to I don't know what I'm doing. It's actually very similar at the end. The values of alpha, the hydraulic diffusivity that we took, is quite similar to what other people have used. So we didn't really cheat too much. The value of T, we constrain it also with this initial slip that was measured at the value. After, it's not a control experiment. So in that case, you see, the rupture can go 1 kilometer from the injection point. If that was your question was more for hydraulic fractures in unconventional, fractures of 500 to a kilometer long is not uncommon. In horizontal extent.
Just to add on to the question, for hydraulic fracturing means your diagram shows the maximum and the minimum horizontal stress in 3 dimensions, and does the axial stress have a control on the propagation of the hydraulic fracture?
Usually, I would reply not to the first order. Okay, so we don't see an effect of that. It's really the hydraulic fractures are tensile fractures, so they minimize energy. So they want to propagate in the direction of the maximum horizontal stress and perpendicular to the minimum stress. The other component of stress, it will play a role when you hit a material with a different properties, let's say elastic modulus, where you will have possibly some local stress rotation. And then the fracture front will exhibit mixed mode, like mode 2 and 3 on top of tensile mode. And then usually you even have cases of dikes that propagate horizontally, but with different layers where you have kind of segments. And that's due to this stress rotation, local stress rotation on the fracture front that splits itself. Yeah.
I have a few questions. One is about this locking front. You were saying that you have in mind some experiment to check it, or you're doing something, but could you comment more on this?
Yes, so I've tasked students first to do this, okay. And because at some point we stop the injection in a lab, we might see this. But first we're trying to do this. It's not easy because you're trying to have something at a scale of 25 centimeters or 20-30 centimeters on the plane of the, so that we could put some gauge of pore pressure on the pre-existing front at different distance from the injection, and also hopefully get with acoustic emission the localization of the rupture front. So I hope I will be able to get, probably in 1 or 2 years we may have some, but it's quite complicated.
But how do you expect to see the front itself?
So we could try to. So in the critically stressed, we will try to do a case kind of dry, because in the critically stressed, if you remember that picture, which is this one, you see the pore pressure disturbance is very localized, so you could model it as a point force. And if we use some PDMS or or PMMA, we can, with a difference of intensity of light, you can, some people have measured a frictional front like that. So our idea is to do that in that case. In the case, if we want to go towards more rock, we hope with acoustic emission we might see something. Or if we put, gouge which are emitting more acoustic emission, we will try. I'm not sure it's going to work.
I have another question. It's about it's kind of a real fault geometry, which could be multi-scale and so on, as you know. But one important consequence is that it might channel the flow in quasi 1D channel.
In 3D, yeah.
And then my question is, how do you expect such a 1D channeling for the fluid part could impact your front dynamic or something?
So far we only do 2D, so we want to be able to move to 3D. So what we see in 2D is that if we are marginally pressurized, then the percolation number of the network is the first order parameter. It's really, everything is about flow. And when you're critically stressed, it's really stress transfer. So it's a cascade of stress transfer. In 3D, I imagine that will be the same. But which means that in a critically stressed, maybe this may not have a first order effect. But if you're marginally pressurized, yes, as you can imagine, this kind of effect of channeling or 1D or the flow heterogeneity will govern everything in the marginally pressurized case. And mechanics will just be a slave of that. So I suspect in the marginally pressurized case, the details of the flow pattern and the characterization of the network is first order effect.
So the last question. Well, since we are coming to the end, we may first thank all the speakers from today.